Hello and welcome to Sleepy Science. Tonight, you're stepping into quantum paradoxes your brain was never built to understand. Three particles can seem to avoid sharing two boxes. A particle can appear separated from one of its own properties. Cause and effect can lose their normal order. Probabilities can become negative. Energy can behave in ways that seem backward, and quantum systems can remember states that should have vanished. These are not made-up puzzles. They come from real quantum theory and experiments that expose where everyday logic stops working. Over the next 4 hours, you'll explore 30 of the strangest paradoxes in modern physics, and each one will push your intuition a little further past its limits. Before we begin, like the video and subscribe, then get comfortable, let your thoughts slow down, and see how long your common sense survives. The quantum pigeonhole effect. 3 particles can fit into 2 boxes without any 2 sharing one. There is a rule so simple that you probably understood it before you ever learned to count. If you have 3 little objects and only 2 boxes, at least one box must contain 2 of them. Put 3 apples into 2 baskets, 3 children into 2 rooms, or 3 pigeons into 2 nests, and there is no escape from that conclusion. Something has to share. This idea is called the pigeonhole principle, and in ordinary life, it is not merely a good guess. It follows directly from counting, but now shrink those pigeons until they are quantum particles. Replace the wooden boxes with 2 possible quantum paths, and something deeply strange appears. Under a very carefully arranged set of conditions, scientists can prepare 3 particles so that when they ask whether any chosen pair occupied the same box, the answer comes back no. Choose the first and second particles, different boxes. Choose the first and third, different boxes. Choose the second and third, different boxes. Your mind immediately protests, because 3 things cannot be placed into 2 places without some pair sharing. And that protest is exactly why the quantum pigeonhole effect is so useful. It reveals that the problem is not arithmetic. The numbers have not changed. What has changed is what it means to say where a quantum particle was before you checked. To see why, imagine that each particle begins without being forced into just one of the 2 boxes. Instead, the experiment prepares it in a quantum state connected with both possible boxes. This does not mean that the particle is secretly sitting in one box, while scientists simply do not know which one. Quantum theory describes the possibilities together, and those possibilities can later combine and interfere with one another. The experimenters then perform another carefully chosen measurement at the end and keep only the runs that finish in a particular final state. This last step is called post-selection, but the idea is simple. Imagine doing the same strange game many times and saving only the rounds that end in one specific way. Now look backward at those saved rounds and ask a very particular question about 2 particles in the middle of the experiment. Were these 2 in the same box? For the selected runs, quantum mechanics predicts that a chosen pair will not be found together. The surprising part is that the same prediction applies whichever pair you decide to test. Experiments using photons have demonstrated the correlations behind this effect, showing that this is not just a puzzle invented on paper. But there is an important detail that keeps the story honest. You cannot open every quantum box, check every pair one after another, and then claim you have taken a normal photograph of 3 particles all sitting separately inside only 2 boxes. Measuring one relationship can disturb the quantum state and change what later measurements can reveal. So the paradox does not mean that 3 tiny solid balls literally squeeze into 2 ordinary containers, while somehow never sharing one. It means something subtler and, in many ways, more interesting. The classical picture in which every particle carries a definite hidden answer to every possible question does not work here. In everyday counting, you imagine that all 3 objects already occupy definite places before you inspect them. If 2 are together, that fact remains true whether you look or not. Quantum experiments do not always allow you to tell that kind of story. The answer you can obtain depends on the entire experimental arrangement, how the particles were prepared, which relationship you choose to test, and which final results you keep. This is why the effect is sometimes described as a violation of the pigeonhole principle. Although physicists continue to debate the best way to interpret what exactly is being violated, the safe conclusion is not that mathematics has failed. 3 ordinary pigeons still cannot sit in 2 ordinary holes without sharing. The lesson is that quantum particles cannot always be treated as ordinary pigeons carrying ordinary pre-existing locations. Their relationships can be shaped by interference in ways that classical objects cannot reproduce. Think about how strange that really is. The experiment is not asking nature a difficult question about distant galaxies or invisible dimensions. It is asking something a child could understand. Are these 2 together or apart? Yet, at the quantum level, even that simple question cannot always be separated from how you ask it. A pair can behave as though it was separated, another pair can behave as though it was separated, and the remaining pair can do the same. Even though trying to combine all those answers into one ordinary picture leads you straight into contradiction. The mistake is assuming that the answers must belong to one hidden classical scene waiting behind the experiment. Quantum mechanics warns you that there may be no such scene. There may only be the different questions nature allows you to ask, and the patterns that appear when those questions are asked in compatible ways. That is what makes the quantum pigeonhole effect more than a clever trick. It shows you how easily common sense can smuggle assumptions into reality without noticing them. You assume objects must always possess definite properties because every large object around you seems to work that way. You assume relationships between things must already exist before you test them because that is how baskets, rooms, stones, and birds behave. But the quantum world was never required to inherit the rules your brain learned from large objects. At its smallest scales, nature can organize possibilities through interference rather than through the simple hidden arrangement you instinctively picture. And perhaps the quietest lesson is also the deepest. Sometimes a paradox does not mean nature has contradicted logic. Sometimes it means you asked nature to fit inside a picture that was too small for it. 3 particles, 2 boxes, and a question that sounds almost childish are enough to expose that boundary. The counting remains simple. The universe does not. The quantum Cheshire cat, a particle can seem to separate from one of its own properties. A cat disappears, yet somehow its grin is still hanging in the air. And quantum physics has a real experiment whose nickname comes from exactly that impossible image. The quantum Cheshire cat does not mean that a tiny particle literally tears itself apart or leaves one of its properties floating alone in space, but it does reveal something almost as strange. Under carefully prepared conditions, measurements can make it look as though a particle travels through one path, while a property belonging to that particle appears along another. To understand this, picture a single neutron entering a device where its journey can split into 2 possible routes before the paths meet again. A neutron is a tiny particle found inside atomic nuclei, and it also carries a quantum property called spin. You do not need to imagine spin as a little ball physically turning. It is simply one of the built-in characteristics physicists can measure, much like an object having a certain label that affects how it behaves. Normally, you would expect a simple rule. Wherever the neutron goes, its spin must go with it. A red toy cannot walk into one room while its redness walks into another. Yet researchers discovered that quantum measurements can produce a much stranger pattern. In one famous neutron experiment, very gentle measurements suggested that the neutron itself was associated mainly with one path, while its spin showed its influence mainly in the other path. This is where the Cheshire cat name comes from. The cat seems to be in one place, while the grin seems to be somewhere else. The word seems is extremely important. Physicists are not saying they caught a spin floating freely without a particle carrying it. The experiment uses something called a weak measurement, which is designed to disturb the quantum system as little as possible. Instead of strongly asking, "Where exactly is the neutron?" and forcing a clear answer immediately, a weak measurement gathers a tiny hint from many repeated trials. One result tells you almost nothing, but thousands of results can reveal a pattern. The researchers then compare those patterns after selecting particular final outcomes. When the experiment is arranged correctly, The statistics can behave as though the neutron and one of its measurable properties took different routes. Similar versions have been demonstrated with light, where the photon plays the role of the cat and polarization plays the role of the grin. But this is also where the story becomes more interesting than the headline, because scientists still debate how literally the effect should be described. Some researchers argue that saying a particle has been separated from its property is too dramatic. From this view, the strange result comes from the way quantum possibilities interfere and from what weak measurements actually tell us. The neutron and its spin have not become two independent objects. The mathematics gives different measurement signals to different paths, but that does not necessarily mean nature contains a naked property wandering around without its particle. And that distinction matters because quantum physics becomes less mysterious when you stop forcing it to behave like everyday objects. A property such as spin is not a sticker glued onto a neutron. It is part of the quantum description of the entire system, including the paths the neutron may take and the way those paths later combine. The experiment therefore teaches you something deeper than particles can lose their properties. It teaches you that the connection between an object and what you can say about that object is not always as simple as it seems in ordinary life. In your world, a bell and its sound, a lamp and its light, a person and their shadow seem naturally tied together because large objects behave in stable, familiar ways. At the quantum scale, however, the information you obtain about a system can be distributed through different possible paths in ways that have no easy everyday picture. The neutron is not secretly playing a magic trick behind the equipment. Rather, your ordinary idea of the thing is here, so every feature of the thing must also be here in exactly the same way, stops being a complete description. And perhaps that is the quiet power of the quantum Cheshire cat. It does not ask you to believe that properties become ghosts. It asks you to notice how much of your understanding of an object comes from assumptions built for the large world you can touch. At the smallest scales, nature can arrange information so strangely that even the simple question, where is the particle and where is what belongs to it, no longer has the kind of answer your intuition expects. The cat has not truly vanished and abandoned its grin, but after you understand the experiment, you may begin to wonder whether a particle and its properties were ever separate little pieces in the first place, or whether that was simply the picture your mind found easiest to hold. Indefinite causal order. Two events may have no definite answer to which happened first. You are used to believing that every story, no matter how complicated, must hide a first step somewhere. The match is struck before the flame appears, the glass falls before it breaks, and one event must come before another, even if you were not there to watch it. Physics usually agrees with you. If two operations happen to the same object, you can normally arrange them into a timeline and say which came first. But some quantum experiments force scientists to consider a stranger possibility called indefinite causal order, where the process cannot always be described as having one ordinary fixed sequence from beginning to end. This does not mean that yesterday can suddenly happen after tomorrow, that effects appear before their causes in everyday life, or that a scientist can send a message into the past. The idea is much more precise. Imagine a tiny quantum system that must experience two operations, which we can simply call A and B. In a normal experiment, there are only two choices. A acts first and B acts second, or B acts first and A acts second. Even if you hide that choice from yourself, there is still a definite order somewhere in the setup. Quantum physics allows researchers to build situations in which the order itself is controlled by another quantum system. Instead of forcing nature to choose one sequence at the start, the experiment can preserve a combination of the two possibilities. So the process behaves as though the route A then B and the route B then A both contribute to what finally happens. The important word here is not both in the everyday sense of doing one complete experiment twice. It is quantum. The two possible orders can remain connected strongly enough to interfere, meaning the final result can depend on their relationship in a way that no simple lottery between two ordinary timelines can reproduce. If you secretly flipped a coin and used heads for A first and tails for B first, you would merely have ignorance about a definite order. Indefinite causal order is different because the experiment can preserve quantum coherence between the alternatives. That difference matters. Researchers have used light particles and carefully controlled optical devices to demonstrate processes with this kind of order, and one of the best-known examples is the quantum switch, where the sequence of two operations is linked to another quantum degree of freedom. Scientists study these systems partly because they challenge an assumption so basic that we rarely notice we are making it, that every physical process must fit inside a single pre-written causal sequence. They are also useful because indefinite order can sometimes provide advantages in tasks involving communication, computation, or learning properties of unknown operations. In certain carefully designed problems, a quantum process can accomplish a task with fewer uses of the available operations than a strategy restricted to one fixed order. That does not make quantum computers magical machines that ignore cause and effect. It shows that the structure connecting events can itself become a resource. There is another subtle point that keeps this idea honest. Physicists do not all use the phrase, "no event happened first," in exactly the same way, because experiments must still be performed inside ordinary laboratories with clocks, detectors, cables, and definite records. What becomes indefinite is the causal order assigned to particular quantum operations within the process, not necessarily every ordinary event surrounding the experiment. Some experiments demonstrate a coherent superposition of different orders, while even more general theories ask whether nature could contain causal structures that cannot be reduced to any fixed order at all. Those are related ideas, but they should not be carelessly treated as identical. And this is where the subject becomes quietly unsettling. You normally imagine time as a shelf and events as books placed on it one after another. Even when you do not know the arrangement, you assume the books already have positions. Indefinite causal order suggests that, at least for certain quantum processes, nature may not always supply that hidden arrangement in the simple form you expect. The order can become part of the physical uncertainty, rather than merely something you have failed to discover. That forces you to ask what before really means. Is it always a basic ingredient of reality? Or can it sometimes emerge only when a process becomes definite enough to leave an ordinary record? We do not yet have evidence that the large world around you loses its familiar causal structure, and your daily life remains stubbornly ordered. You wake before you leave the house. You speak before someone hears your words, and broken cups do not leap upward and become whole. But deep inside carefully controlled quantum experiments, the universe seems willing to loosen a rule you probably thought was untouchable. It may not always begin by deciding which event comes first. Sometimes the order itself is part of what remains open. And perhaps that is the real lesson. Reality can be stranger, not because it breaks logic, but because it refuses to promise that the timeline you instinctively draw is always there before you draw it. The quantum switch. An experiment can perform A before B and B before A at the same time. There is a kind of quantum machine that can refuse to decide which instruction should come first, and that simple refusal creates a kind of order that has no ordinary counterpart. Imagine that a tiny piece of information must pass through two operations called A and B. You do not need to know what those operations are. Think of them simply as two different changes that can be made to the same thing. In the world you know, there are only two possibilities. A happens first and B happens afterward, or B happens first and A happens afterward. You can hide the order, randomly choose the order, or forget the order, but somewhere there is still a real sequence. The quantum switch does something more unusual. It uses one quantum system to carry the information being changed, and another quantum feature to control the order in which the changes occur. If that control is prepared in the right quantum state, the experiment does not simply choose A before B or B before A. Instead, both possible orders remain part of one coherent quantum process. One part of the process behaves as though the information experienced A and then B, while another behaves as though it experienced B and then A, and crucially, those alternatives can later meet and interfere. That last detail is what makes the quantum switch much stranger than tossing a coin. If you toss a coin behind your back and use heads for A first and tails for B first, you may not know which sequence happened, but one of them definitely did. The uncertainty exists in your head. In a quantum switch, the two orders can remain physically connected as quantum alternatives, and the final experiment can reveal effects that depend on that connection. Scientists have implemented versions of this idea using individual particles of light. A photon can carry the information researchers want to manipulate, while another feature of that same photon, such as its polarization or its route through the apparatus, can control which operation comes first. The clever part is that the controlling feature itself can be placed into a quantum combination rather than being forced into one ordinary choice. The photon then passes through an arrangement built so carefully that one quantum alternative encounters A before B, while the other encounters B before A. At the end, the alternatives are brought together again. Researchers do not open the device halfway through and ask which sequence the photon followed, because doing that would destroy the very relationship they are trying to preserve. Instead, they examine the final patterns. Those patterns can contain information produced by the coexistence of the two orders, showing that the process cannot be described simply as an ordinary mixture in which A sometimes happened first and B sometimes happened first. Experiments with photonic quantum switches have measured this kind of causal non-separability, the technical phrase for a process that cannot be reduced to a simple collection of definite orders. What makes this especially interesting is that the quantum switch is not merely a philosophical demonstration. The strange ordering can actually be useful. Suppose you are given two mysterious machines and want to learn something about how their actions relate to each other. With ordinary strategies, you may need to send your system through the machines several times in different sequences before you can answer the question. A quantum switch can sometimes obtain the required information using fewer calls to those machines because it lets both orders contribute to a single experiment. In carefully chosen quantum information tasks that can provide advantages in computation, communication, measurement, and the identification of unknown processes. More recent theoretical work has even shown strong separations between what a genuine quantum switch can do with a certain number of uses of unknown operations and what ordinary fixed-order quantum circuits would need in order to reproduce the same transformation. But now comes the part that is easy to exaggerate, and understanding it makes the real phenomenon more interesting rather than less. The quantum switch does not mean a laboratory has escaped time. The scientists still turn on their equipment before they collect the results. The photon still enters the apparatus before it leaves. Nobody receives tomorrow's message yesterday, and nothing in the experiment allows you to return to your childhood or change an event that has already been recorded. Even the phrase, A before B and B before A at the same time, should not be imagined as two clocks somehow showing contradictory histories. What becomes indefinite is the operational order of A and B within the quantum process. The surrounding experiment can still sit perfectly normally on a laboratory table, with wires, mirrors, detectors, and clocks behaving in their familiar direction. This distinction is one reason researchers are careful when interpreting these experiments. Different physical implementations can arrange paths and control systems in different ways, and scientists continue to study exactly what should count as the strongest demonstration of indefinite causal order. The safest claim is also astonishing enough. Quantum mechanics allows the order in which transformations act to become a coherent quantum resource rather than a fixed background instruction. And once you understand that, something subtle changes in the way you think about a process. You normally imagine that objects may be uncertain while the order of events remains solid. A coin might have an uncertain outcome. A particle might have an uncertain property. But you rarely question the stage on which those uncertainties unfold. First this, then that. The sequence seems deeper than the things moving through it. The quantum switch shows that quantum theory can push uncertainty one level higher. It is not only asking what happens to a system, It can place the arrangement of operations themselves into a quantum structure. The order becomes part of the information being manipulated. That is why physicists sometimes describe the quantum switch as a higher-order process. Instead of merely transforming a particle, it transforms the way other transformations are connected. And perhaps this is the most valuable thing it teaches you. Nature does not have to organize every small process using the same kind of instruction list you would write on a piece of paper. Your mind likes steps, because steps are how you cook food, build houses, tell stories, and remember your day. Step 1 must stand above step 2. But at the quantum level, the relationship between steps can itself become something that can be controlled, combined, and tested. A and B do not disappear. Cause and effect do not become meaningless. Time does not collapse into chaos. Something quieter happens. The universe reveals that even the word before may sometimes describe a physical resource rather than an unquestionable backdrop. And when two possible orders can contribute to one experiment and leave a measurable signature behind, you are left with a strange but precise lesson. The smallest machines in nature may not always need to choose the order of their instructions before they begin. Quantum time reversal. Some processes can behave as though their direction through time is undecided. A broken glass never gathers its pieces from the floor, leaps back onto the table and fills itself with water again. So, everything you have ever seen quietly teaches you the same lesson. Time has a direction, and there is no button for reverse. You remember yesterday, but not tomorrow. Smoke spreads through a room but does not naturally squeeze itself back into a candle. Your body grows older rather than younger. Yet when physicists look beneath this familiar world and study the basic rules governing tiny quantum systems, the arrow becomes less obvious. Many fundamental quantum processes can be described by laws that remain meaningful when their time direction is reversed. This does not mean particles are secretly traveling into yesterday, and it certainly does not mean scientists have invented a time machine. It means something much more careful. If a certain quantum transformation takes an initial state and changes it into another state, physics can sometimes define a corresponding reverse transformation that undoes or mirrors that evolution. It is a little like watching a perfectly reversible dance. If you filmed two dancers performing a sequence and then played the recording backward, every step could still form a physically sensible dance. A melting ice cube is not like this because heat spreads into the surroundings and countless tiny details become practically impossible to recover. But a carefully isolated quantum operation can come much closer to a reversible sequence. For a long time, however, there was still an ordinary assumption hidden inside the laboratory. Even if a process could be studied in a forward direction or represented in a reverse direction, the experiment would use one direction at a time. Researchers then asked a far stranger question. What if the direction itself could be placed into a quantum combination? What if a device did not have to be used simply as a forward process or simply as its time-reversed counterpart, but could participate in a single experiment in which both descriptions remained coherently connected? This idea is known as an indefinite time direction, and one important example is called the quantum time flip. The name sounds as though a particle has been thrown backward through history, but that picture is misleading. What is being flipped is the way a quantum operation is accessed. Imagine a tiny machine with two ends. Used one way, it performs a certain transformation. For suitable quantum devices, using the corresponding reverse description produces the time-reverse version of that transformation. Now add a quantum control that does not force the experiment to select only one of those possibilities. The resulting process can preserve a coherent combination of the operation and its reverse. In other words, the direction is not merely unknown because someone forgot to look. If you secretly chose forward or backward with a coin, there would still be a definite direction in every run. Here, the alternatives can remain linked strongly enough to produce interference, allowing the final result to contain information that would not appear from an ordinary random mixture of forward and reverse experiments. Physicists moved this idea from theory into the laboratory using photons, tiny packets of light. In a 2024 experiment, researchers built an optical implementation of the quantum time flip and demonstrated a coherent superposition of a quantum evolution with its time reverse. The experiment used specially designed optical components so that a quantum operation could be accessed in the two relevant directions, while another quantum feature controlled how those possibilities were combined. The scientists then tested the device with a task in which it had to distinguish between different kinds of unknown transformations. A system forced to use only one fixed time direction could not perform the task as well. Even more surprisingly, the quantum time flip achieved an advantage that was not explained simply by rearranging the order of ordinary operations. The resource came specifically from having access to the coherent relationship between a process and its reversed version. That makes indefinite time direction interesting, not only because it sounds strange, but because it can carry useful information. Researchers are now studying whether such structures could help with quantum measurement, communication, and precision sensing. The important lesson, though, is what the experiment does not show. A photon does not emerge from the detector before it enters the laboratory. Scientists are not receiving answers from the future. The experiment does not make breakfast return to an egg or cause yesterday's decisions to disappear. The ordinary arrow of time you experience is strongly connected with thermodynamics. Large systems contain enormous numbers of particles, and their energy and information tend to spread into more disordered arrangements. Once cream has mixed into coffee, there are unimaginably many microscopic details you would have to control to separate it perfectly again. That is why macroscopic reversal is so different from reversing a carefully controlled quantum operation. The quantum experiment deals with a tiny, engineered process where coherence can be preserved, not with reversing the history of the surrounding universe. There is another subtlety worth understanding. Saying that a process has an indefinite time direction does not necessarily mean that time itself has become directionless. The laboratory still has a clock. The experiment begins, equipment operates, detectors record results, and the scientists later read those results. What becomes indefinite is a specific relationship between a quantum transformation and the direction in which that transformation is probed. That distinction protects the science from turning into science fiction, but it also leaves something genuinely unsettling behind. You usually think of the arrow of time as part of the furniture of reality, something so basic that everything else must obey it. Past sits behind you, future waits ahead, and every process seems to inherit that direction automatically. Quantum theory suggests that this certainty may belong more strongly to the large world than to the deepest description of every physical operation. At very small scales, under very special conditions, forward and reverse can become alternatives that quantum mechanics treats together, rather than choices that must always be separated beforehand. The world around you still ages, breaks, cools, forgets, and moves toward tomorrow. Nothing about this experiment changes that. But underneath that irreversible surface, physics contains transformations that remember a quieter symmetry, one in which the difference between going forward and describing the reverse is not always as absolute as your experience makes it feel. And perhaps that is the most thought-provoking part of quantum time reversal. It does not promise that you can return to the past. It asks a stranger question instead. If the deepest rules can sometimes hold forward and reverse within one quantum description, then perhaps the one-way river of time you feel every second is not the first rule written into nature, but something that becomes clear only when the tiny reversible pieces of the universe gather together into the enormous, irreversible world you call home. Entangled histories. Different possible pasts can become quantum connected. What if the past of a single particle were not one invisible trail waiting for you to discover, but several possible stories woven together so tightly that asking which story happened would be like trying to separate the threads after they had already become the fabric? This is the idea behind entangled histories, one of the stranger ways physicists have learned to describe quantum systems across time. The word history sounds ordinary, but here it has a very specific meaning. Imagine watching a tiny system at 3 different moments, early, middle, and late. At each moment it might have one property or another. In everyday life, you would simply connect those moments into a sequence. A toy car was on the table, then on the floor, then inside a box. Even if you missed the middle part, you would assume that one definite sequence of events actually occurred. Quantum physics does not always let you make that assumption so easily. Instead of describing only what a system is like at one instant, physicists can describe an entire possible sequence of states across several moments as one object called a quantum history. Now comes the unsettling part. Just as ordinary quantum states can be linked in ways that cannot be separated into independent pieces, different parts of a history can also become linked across time. The early state, the middle state, and the later state may form a single pattern whose correlations cannot be explained by saying that the system simply possessed one definite property at each stage. In that sense, the history itself can be entangled. This does not mean yesterday is physically tied to tomorrow by an invisible rope, and it does not mean that a particle can go back and rewrite something that already happened. It means that when you ask certain questions about what the system did at several different times, quantum theory can give you correlations that belong to the whole sequence rather than to a set of separate moments. A useful way to picture this is with a very simple story. Imagine a lamp that can appear red or blue at 3 different times. In a classical world, even if you never looked at it, you would assume there was some actual hidden sequence, perhaps red, red, blue, or blue, red, blue, or one of the other possibilities. You might not know which sequence occurred, but you would believe one of them did. An entangled quantum history is stranger. The best description may involve a combination of different temporal sequences, and those sequences can interfere with one another. You cannot always say that one complete hidden story was simply waiting behind the measurements. The relationships between the moments can carry information that no collection of ordinary, separate histories can reproduce. Physicists have tested this idea experimentally using a single photon, a tiny packet of light, and its polarization, which you can think of simply as an orientation-like property of the light. Instead of entangling several different photons spread across space, researchers prepared and measured the polarization of one photon across 3 different times. The correlations they observed matched what is called a GHZ-type entangled history and strongly exceeded the limit expected for histories that could be broken into independent temporal pieces. That result is fascinating because there is only one traveling photon in the experiment. The strange connection is not mainly between separate objects sitting far apart. It appears between different stages in the evolution of the same system. The photon has an earlier chapter, a middle chapter, and a later chapter. Yet quantum mechanics can describe those chapters as parts of one inseparable temporal structure. This gives you a new way to think about what a measurement actually tells you. Suppose you find footprints outside your house, wet marks inside the hallway, and an umbrella leaning near the door. In normal life, you reconstruct a history. Someone walked through rain, entered the house, and left the umbrella behind. The clues point backward toward a sequence of events that you assume already happened in one definite way. Quantum experiments make this reconstruction much more delicate. A measurement made now can give you information about a system's earlier behavior, but the past you reconstruct may not always be expressible as one simple list of properties that existed independently at every moment. Some questions about the history can be answered together, while other questions correspond to different ways of dividing the quantum possibilities. This is one reason the entangled histories framework was developed. It lets physicists treat entire sequences of events as things that can be studied, compared, and measured instead of pretending that quantum mechanics only speaks about isolated snapshots. The framework is mathematically compatible with ordinary quantum theory. It is not a replacement for quantum mechanics or a new law of nature. Its value is that it makes temporal structure visible in a way that the usual description can hide. And there is a subtle lesson here that is easy to miss. When you hear different possible pasts, you might immediately imagine parallel universes, alternate childhoods, or histories branching behind you like roads. That is not what these experiments have shown. An entangled history is not proof that several macroscopic paths literally happen to you. It is a quantum description of correlations between possible sequences of states in a controlled physical system. The experiment does not tell you that a photon had several complete secret biographies and then chose one when scientists looked. It tells you that trying to assign an ordinary biography to every stage can fail to capture the measurable structure. The whole history can matter more than any isolated frame. Think of a melody. If you freeze it at one instant, you do not have a melody at all. You have one sound. The music exists in the relationship between notes across time. Change the order or the connections, and you change what the music is. An entangled quantum history is not literally music, but the comparison helps reveal what makes the idea unusual. The important physical information can belong to the pattern across moments rather than to each moment separately. That possibility has consequences for how physicists think about time-dependent measurements, quantum information, and even the meaning of a physical record. Most of what you call the past is never directly accessible anyway. You see photographs, fossils, scars, memories, light arriving from distant stars, and marks left on instruments. From those present records, you infer what happened before. In ordinary life, that works so reliably that you forget you are reconstructing anything at all. You simply say, "That happened." Quantum theory asks you to be more careful. For certain microscopic systems, there may be no single classical chain of hidden properties capable of explaining every correlation you can later measure. The evidence can point not toward one ordinary sequence, but toward a quantum structure made from several possible sequences connected as one whole. And that does not make the past unreal. It makes the idea of a past more precise. It tells you that what happened may be a deeper question than where was the particle, or what property did it have, because sometimes the answer belongs to the relationship between moments. You still woke up this morning. The room you left behind still has a history. Your memories do not suddenly become quantum superpositions simply because photons behave strangely in laboratories. The large world has countless interactions that rapidly destroy these delicate temporal relationships and leave behind stable records, which is why your life appears to possess a clear sequence. But beneath that familiar clarity, nature allows something more subtle. A quantum system can carry a history whose pieces cannot always be pulled apart into separate facts about separate times. And once you understand that, the past begins to look a little less like a row of frozen photographs, and a little more like a structure whose meaning can live in the connections between the frames. Perhaps that is the quietest surprise of entangled histories. Quantum mechanics does not merely make the present uncertain. Under the right conditions, it can make the very grammar we use to tell a story about the past too simple for the story nature is actually telling. Quantum reference frames. Something can be in superposition for you, but not for another observer. Stand on a train and watch another train glide beside you. And for a few strange seconds, you may not know which train is actually moving until you look at the station outside. Physics has always allowed different observers to describe motion differently, but quantum physics pushes this familiar idea into territory that feels almost impossible. A quantum reference frame begins with a simple fact that is easy to forget. Every position you ever describe is a position relative to something else. You say a cup is on the table, a car is 10 meters from a tree, or the moon is far from Earth, but there is no giant invisible ruler attached to the universe telling everything where it absolutely is. You choose something as your reference and describe other things relative to it. In ordinary physics, this causes no great trouble because the reference object itself can usually be treated as having a clear position and motion. A laboratory floor makes a good reference because you do not expect the floor to be spread across several locations. But what happens if the thing you use as your reference is itself a quantum object? That question creates the idea of quantum reference frames. Imagine a small particle, which we will call Alice, and a laboratory, which we will call the lab. From the lab's point of view, Alice has been prepared in a superposition of two locations. In simple language, the quantum description includes one possibility in which Alice is here and another in which Alice is farther away, with both possibilities remaining part of the same state. It would be tempting to say that being in two places is simply a permanent fact about Alice. But now perform a strange change of perspective. Instead of using the lab as the ruler against which everything is measured, use Alice herself. From Alice's quantum reference frame, Alice does not need to be described as floating between two positions relative to herself. She sits at the center of her own coordinates, just as you always regard yourself as being right where you are. The surprising part is what happens to the lab. The two-position structure can now appear in the lab's description relative to Alice. In one branch, the lab lies one distance away. In another branch, it lies somewhere else. What looked like Alice is in a superposition from one frame can become the lab is in a superposition relative to Alice from another. Nothing physically jumped when you changed descriptions. No particle noticed you thinking about it. No human consciousness reached into the experiment and rearranged reality. You changed the quantum reference frame. Much is changing from the platform's view to the train passenger's view, changes which object you describe as moving. The quantum version is richer because the transformation can involve superpositions rather than only ordinary velocities and positions. This leads to a remarkable conclusion. Superposition is not always a property that can be attached to an object without mentioning what the object is being compared with. In some situations, it is relational. The question, is this particle in a superposition of positions, may be incomplete in the same way that asking, is this car moving, is incomplete until you say moving relative to what? Relative to the road, the car moves. Relative to the person sitting beside you in the same car, you may remain nearly still. Quantum reference frames suggest an analogous lesson for some quantum properties. Although the quantum case has mathematical features that ordinary motion does not, the idea becomes even clearer if you add a third object. Suppose Alice is spread between two locations relative to the lab, while another particle, Bob, is positioned in a particular relationship with Alice. From the lab's description, the arrangement may involve superposition and correlations between Alice and Bob. Switch into Alice's quantum reference frame, and those features can be redistributed. Something that looked like superposition in one place can appear as a different superposition elsewhere, and relationships that looked complicated from one frame can become simple from another. Even entanglement in appropriate setups can depend on which quantum system is chosen as the frame. This does not mean physicists can make facts true or false simply by changing their minds. Every observer must still agree on predictions for actual physical comparisons when those predictions are translated correctly between frames. The disagreement is in the description, not in whether an experiment produces a real result. Think again about two people describing the same room. One measures every object from the left wall and another measures everything from the right wall. They will write different numbers, but if they understand how their coordinate systems relate, they will never disagree about whether two chairs touch. Quantum reference frame transformations aim to do something similar when the wall you choose as your origin is itself allowed to behave quantum mechanically. This matters because reference frames are not really abstract grids floating outside nature. A reference frame is ultimately built from physical things: clocks, rulers, atoms, light signals, laboratories, planets, or people holding instruments. And if every physical thing is quantum at a sufficiently fundamental level, then treating reference frames as perfectly classical forever may be only an approximation. Usually, it is an astonishingly good approximation. Your room does not visibly smear across different locations, because interactions with the enormous surrounding environment rapidly destroy delicate, large-scale quantum coherence. But researchers interested in quantum gravity, quantum communication, and the foundations of physics cannot always assume that there is a perfectly classical observer standing outside the universe with an absolute ruler. They need ways to describe physics when the reference system itself participates in quantum behavior. This is one reason quantum reference frames have attracted so much attention. They offer a language for asking what one quantum system would say about another without secretly relying on an external, perfectly fixed stage. They may also help researchers think about more difficult situations where gravity and quantum mechanics meet, because Einstein's theory already teaches that space and time are described relative to physical observers, while quantum theory teaches that physical systems can occupy superpositions. Combining those lessons raises a difficult question. What does a coordinate system mean when the thing carrying the coordinate system has no single classical state? Quantum reference frames do not yet solve quantum gravity, and it would be misleading to pretend that they do. They are a developing theoretical framework for making such questions precise. There is also no evidence here that two human beings can look at the same ordinary object and magically place it in different realities. The observer in quantum reference frame theory is often simply a physical system used as a reference, not necessarily a conscious mind looking through a pair of eyes. That distinction matters because otherwise an elegant piece of physics can quickly turn into a mystical claim it never made. The deeper lesson is quieter. You grow up imagining that objects carry their descriptions around like labels. This particle is here. That particle is moving. This one is in a superposition. Quantum reference frames suggest that some of those labels may belong not to an object alone, but to a relationship between objects. Change the system from which you describe the world, and the location of the quantum strangeness can change with it. From one frame, the particle appears spread across possibilities. From another, that particle can become the stable center, while something you previously considered ordinary inherits the superposition instead. Yet after translating the descriptions correctly, the physics remains consistent. And perhaps this is what makes the idea so quietly unsettling. The universe may not contain a single privileged seat from which its deepest state is revealed exactly as it really is. There may instead be physical systems describing other physical systems, each perspective connected to the others by precise rules. You are accustomed to asking where the quantum uncertainty is located, as though uncertainty must belong to one particular thing. Quantum reference frames invite a different question, uncertain relative to what? And once that question becomes unavoidable, even the simple idea of an object having a state begins to look less like a private possession and more like a relationship written between parts of the universe. The Leggett-Garg puzzle. A system may refuse to have a definite history between measurements. A coin sitting quietly under a cup seems to have only two honest possibilities: heads or tails. And even if you refuse to look, you naturally assume one of those answers is already there. That assumption feels so harmless that you probably never notice you are making it. Yet the Leggett-Garg puzzle was created to test whether nature always works that way. In the 1980s, physicists Anthony Leggett and Anupam Garg asked a deceptively simple question. If a physical system can exist in two distinguishable states, should we be allowed to believe that it always possesses one definite state at every moment, even when nobody measures it? Their idea was aimed at what they called macro-realism, the everyday view that large ordinary things have real properties whether or not anyone checks. A cat is either in the kitchen or the bedroom. A light is either on or off. A compass needle points one way or another. You may not know the answer, but ignorance is not the same as the answer failing to exist. Leggett and Garg wanted to know whether this common sense picture could survive when tested against quantum systems. To do that, they proposed looking not at two objects separated in space, but at one system measured at different moments. Imagine a tiny object that can be in one of two states, which you can picture simply as left or right. You check it at one time, then later again. If the object always has a definite state between those checks, and if it is possible in principle to observe it without secretly changing what it was going to do, then the correlations between those measurements must obey certain limits. These limits are called Leggett-Garg inequalities. You do not need the equations to understand the idea. They are like a consistency test for a hidden story. If the system really was always left or right at every moment, then all the answers collected at different times should fit together like pages from one ordinary diary. There are only so many ways those pages can agree or disagree. Quantum mechanics predicts that, under the right conditions, the measurements can violate that limit. Experiments have observed such violations in systems including superconducting circuits, photons, nuclear spins, and other carefully controlled quantum devices. This is what makes the results so uncomfortable. The data can resist the idea that the system simply carried a normal, definite value through the unobserved time between measurements. But there is an important trap here. You cannot jump from this result to the dramatic statement that the particle definitely had no state when nobody looked. The Leggett-Garg test challenges a combination of assumptions, not one isolated belief. One assumption is macrorealism. The system always has a definite value. Another is often called non-invasive measurability. You could, at least in principle, find out that value without disturbing the system's future behavior. That second assumption is difficult to guarantee in quantum experiments, because measurements can interact with the system. If you check something and your checking changes it, then strange later results might come from the disturbance rather than from the absence of a definite earlier state. This creates what physicists call the clumsiness loophole. Perhaps the experiment only looks mysterious because the measuring device is clumsy. Researchers have developed clever methods to reduce this problem, including weak measurements and protocols designed so that, under a classical picture, certain measurements should not need to disturb the system at all. Some experiments have produced strong evidence against simple macro-realistic explanations. But physicists remain careful about exactly which assumptions each test rules out. That caution is part of the science, not a weakness in it. The deeper lesson is that quantum mechanics does not always allow you to tell the same kind of story you tell about a hidden coin under a cup. A classical coin may have an unknown face, but you imagine the face exists continuously while you are not looking. A quantum system can evolve in a way where that simple picture does not reproduce the observed temporal correlations. The difference becomes clearer if you imagine a tiny bell that can ring in one of two tones. You listen at noon, again a moment later, and then once more. In an ordinary model, the bell had one tone or the other throughout the entire sequence, even during the silent gaps when you were not listening. If you collect enough trials, the pattern of answers must respect the fact that one definite story connected all three moments. A violation of the Leggett-Garg inequality says that the pattern cannot be explained so easily under the assumptions of macrorealism. The system behaves less like a hidden answer waiting to be uncovered, and more like a quantum process whose measurable properties are not safely described by a complete classical timeline of pre-existing values. This matters because it moves one of quantum theory's strangest questions away from the usual image of tiny particles being mysterious in space and places it directly into time. The puzzle is not merely where was it, but was there a definite answer at every moment between the times we checked? That is a much more unsettling question, because your entire everyday experience teaches you to assume continuity. When you leave your keys in a drawer and return an hour later, you never imagine that their location became undefined during your absence. The large world behaves so consistently that definite existence feels inseparable from reality itself. Leggett and Garg wanted to test whether that intuition could simply be extended downward into the quantum world. The surprising answer is that nature does not make that extension easy, and there is another reason this puzzle is important. It helps physicists investigate where quantum behavior begins to fade into the ordinary world. Leggett was especially interested in whether truly large systems could ever display unmistakably quantum behavior, or whether something new might appear as objects become more macroscopic. Modern experiments with larger and more controllable quantum systems continue to push on this boundary. Superconducting devices, for example, can involve collective behavior of enormous numbers of electrons while still showing quantum effects under carefully isolated conditions. Tests inspired by Leggett and Garg therefore do more than challenge philosophy. They help probe how far quantum coherence can survive as systems become larger and more complex. Yet none of this means your chair lacks a location whenever you close your eyes. Large objects interact constantly with light, air, heat, vibrations, and countless surrounding particles. Those interactions rapidly destroy the delicate quantum relationships needed for these effects to remain visible, leaving behind the stable world you recognize. The Leggett-Garg puzzle lives in a much more controlled realm, where isolation is strong enough for quantum behavior to persist long enough to be tested. And perhaps that is why its message feels so quiet at first. Nothing explodes. No particle races backward through time. No impossible machine appears. Scientists simply ask the same tiny system a few questions at different moments and compare the answers. Yet hidden inside those answers is a challenge to one of your oldest instincts: that reality must possess a complete set of definite facts at every instant, whether anyone ever checks them or not. Quantum mechanics does not tell you to abandon reality. It asks you to be more careful about what kind of reality you are assuming. Maybe the world beneath your ordinary experience is not made from little objects carrying perfectly completed stories through time. Maybe, at the smallest scales, the story is not always written page by page before the page is opened. And that is what makes the Leggett-Garg puzzle so powerful. It turns a childlike question, what was it doing when nobody looked, into an experiment whose answer still forces physicists to think very carefully about what it means for something to have been real all along. Quantum causality. Without a fixed timeline, cause and effect may not always come in a definite order. Every explanation you have ever trusted seems to lean on one invisible rule. Something happens, and then something else can happen because of it. Push a toy and it rolls. Press a button and the light turns on. Speak a word and another person hears it afterward. Cause comes first, effect comes second. And somewhere behind even the most complicated event, you expect there to be a timeline that could, at least in principle, be written from top to bottom. But modern quantum theory allows physicists to ask whether that hidden timeline must always exist at all. The question is not simply whether we know which event happened first. Ignorance is easy. If two people enter a room through different doors and you arrive too late to see them, you may not know who entered first, but one of them certainly did. Quantum causality asks about something more radical. Could there be physical processes for which no description based on one definite causal order is enough, even in principle? To study this, physicists sometimes imagine several small laboratories, each sealed from the others, except for whatever quantum system enters and leaves. Call the scientists inside Alice and Bob. Alice receives something, performs an operation on it, and sends something out. Bob does the same. In an ordinary causal world, the possibilities seem complete. Alice can act first and influence what later reaches Bob. Bob can act first and influence Alice. Or perhaps neither can influence the other because their events are too separated. Even if a coin randomly chooses between these situations, every individual run still belongs to some ordinary causal story. But researchers discovered a mathematical framework in which quantum processes need not begin with any such global story. Instead of first drawing a timeline and then placing events upon it, the framework describes the possible relationships among the laboratories directly. The causal structure itself is no longer assumed in advance. This approach is often called the process matrix framework, and its central idea can be understood without equations. Perhaps the rules connecting events can be more fundamental than a single universal answer to who came first. Imagine two children passing instructions through a strange box. If Alice definitely sends information first, Bob can use that information when choosing his response. If Bob definitely goes first, the influence runs the other way. Classical causal reasoning places limits on how well they can perform certain coordinated tasks when the direction of influence must always be one way or the other. Those limits are called causal inequalities, somewhat like rules saying, if every round has a definite causal direction, your scores can never exceed this point. Some mathematically allowed quantum processes can cross that boundary. Their correlations are too strong to be reproduced by any ordinary mixture of Alice before Bob and Bob before Alice stories. If such a process exists physically, asking which laboratory was the cause and which was the effect would not merely have an unknown answer. The assumption that one of those two answers must exist would itself be wrong. This is much broader than saying that two operations can be placed into a controlled quantum ordering. Here, physicists are investigating the architecture of causality itself. Whether a network of events must sit inside a fixed global sequence before the laws of physics can tell us what happens. And this distinction is important because not every example of indefinite causal structure is equally radical. Some laboratory experiments have already demonstrated quantum processes whose operations cannot be described by one fixed order. But the strongest theoretical examples, those capable of violating causal inequalities in the clearest possible sense, are not yet known to occur freely in nature. They exist consistently inside powerful mathematical models. But whether every such model corresponds to something the universe can actually build remains an open question. That uncertainty is not a weakness. It is exactly where the science becomes interesting. Physics has often advanced by discovering that a rule we treated as a foundation was actually an approximation. Earth once seemed like the unmoving center of everything. Time once seemed universal. Space once seemed like an empty, rigid stage. Now causality itself is being examined with the same suspicion. Perhaps a fixed timeline is fundamental. Perhaps it emerges only when quantum systems become large and interact with ordinary environments. Perhaps a deeper theory combining quantum mechanics with gravity will make causal order flexible in ways current experiments only hint at. General relativity already teaches that space and time are not a rigid background. Matter and energy shape their geometry. Quantum theory, meanwhile, refuses to give every microscopic property one simple classical value. Put those ideas together, and an uncomfortable question appears naturally. If space-time itself must someday be treated quantum mechanically, why should the causal order built from space-time remain perfectly definite? Researchers studying quantum gravity take this possibility seriously, especially in extreme situations where the geometry separating events might itself fail to behave like one classical arrangement. But none of this means that causes disappear, logic fails, or you can create an effect today and freely choose its cause tomorrow. A world with indefinite causal structure still obeys mathematical consistency. It does not grant permission for contradictions. You cannot use these ideas as evidence that decisions can rewrite recorded history, that thoughts send messages backward through time, or that ordinary events happen without reasons. The theory is much narrower and more disciplined. It asks whether the relationship this event can influence that event must always fit into one fixed global order. That sounds technical until you realize what a causal order really gives you. It gives you the skeleton of every story. It allows you to say this happened because that happened earlier. It lets you imagine the universe as an enormous chain of moments, each handing information to the next. If quantum physics can sometimes describe correlations without first supplying that skeleton, then perhaps sequence is not always the deepest layer of explanation. Perhaps some microscopic processes are better understood not as beads placed along a pre-existing string of time, but as a complete network of relationships from which an ordinary before and after structure appears only under certain conditions. You would still wake before eating breakfast. Rain would still fall before the pavement becomes wet, and a message would still need to reach your phone before you could read it. The stable world around you gives causality a beautifully clear direction. Yet beneath that stability, theoretical quantum physics leaves open a stranger possibility. Reality may not always begin by arranging every event into a line. Sometimes the line itself may be part of what physics has to explain. And if that turns out to be true, then cause and effect would not vanish. They would become something even more fascinating. An order that may emerge from a deeper quantum structure rather than a rule the universe was forced to obey from the beginning. Negative quantum probabilities. Physicists sometimes calculate chances smaller than zero. Imagine opening a weather app and seeing a -20% chance of rain. Not cold weather. Not a mistake in temperature, but an actual chance of rain smaller than zero. you would immediately know something was wrong because ordinary probability does not work that way. A probability of 0 means something never happens, while a probability of 100% means it certainly happens. And there is nowhere sensible to go below 0. Yet physicists studying quantum systems routinely use mathematical descriptions in which numbers that look like probabilities can become negative. These are not ordinary probabilities, and the distinction is crucial. Nobody has ever performed an experiment 10 times and watched an event happen -2 times. Negative quantum probabilities are better called quasi-probabilities, special bookkeeping tools that resemble probability distributions, but are allowed to break some of the rules. Ordinary probabilities must obey. Their strange negative values are useful precisely because quantum reality cannot always be squeezed into the kind of hidden classical picture that works for coins, dice, and bouncing balls. To see why, picture a map describing a tiny object. You might want the map to tell you both where the object is and how it is moving. For a normal ball, this causes no conceptual problem. Even if your instruments are poor, you assume the ball has one real location and one real motion at every instant. In quantum mechanics, certain properties cannot be treated that way simultaneously. The obstacle is deeper than simply having bad instruments. The structure of quantum theory does not generally provide one ordinary joint probability table containing definite answers for every incompatible measurement you might choose to make. Physicists therefore invented alternative maps. One of the most famous is called the Wigner quasi-probability distribution. Instead of drawing a particle as a tiny dot, it creates a landscape describing a quantum state using position-like and motion-like information together. Some quantum states produce a perfectly smooth landscape containing only positive values, which can look almost like an ordinary probability map. Other genuinely quantum states create regions below 0. Those dark mathematical valleys are not locations where less than nothing exists. They tell you that no ordinary classical probability story can fully reproduce the patterns stored in the quantum state. Think of it like keeping track of waves using positive and negative numbers. 2 water waves can meet so that one crest cancels another trough. The negative sign does not mean negative water exists. It tells you how different contributions combine. Quantum quasi-probabilities use a related kind of bookkeeping. Positive and negative contributions can cancel when physicists calculate the real probabilities that experiments finally reveal, and those final measurable probabilities always return to the ordinary allowed range. This is why you will never see a detector announce, "There was a negative chance that the photon arrived." The negative number lives inside the representation used to describe the quantum structure before ordinary measurable probabilities are extracted from it. Another important version is the Kirkwood-Dirac quasi-probability, which helps physicists describe relationships between measurements that cannot simply be treated as simultaneously possessing ordinary hidden values. These quasi-probabilities can sometimes become negative, or even take values that are not ordinary real numbers at all. That sounds like mathematical mischief, until you realize that these strange values often appear exactly where quantum behavior becomes impossible to imitate with a simple classical model. In many settings, negativity acts like a warning light telling researchers, "Do not imagine this system as a box containing unknown but perfectly ordinary answers." The system may possess correlations that depend on the measurement context, interference between alternatives, or other quantum structures that cannot be replaced by ignorance about a hidden classical state. This connection has become especially important in quantum information science, because researchers have discovered that negativity in certain quasi-probability descriptions is closely connected with genuinely non-classical resources. In some computational models, if the entire calculation can be represented using only ordinary positive probabilities, a classical computer can efficiently imitate what the quantum machine is doing. When unavoidable negative quasi-probabilities appear, that easy classical picture can break down, which is one reason physicists study negativity as a possible marker of where useful quantum power comes from. But negative quasi-probability is not a magical certificate that automatically proves every possible kind of quantum advantage. Different quasi-probability representations answer different questions, and scientists must be careful about what kind of negativity has been observed and what conclusions it supports. Even the same quantum state can look different when described through different mathematical representations. That makes the idea more subtle than simply saying negative means quantum. What remains remarkable is that trying to preserve the familiar structure of ordinary probability forces these unusual numbers to appear again and again. Quantum theory seems to be telling you that classical probability is sometimes too small a language for the job. You can understand this with an imaginary bag of colored stones. Suppose someone tells you there are 10 stones inside and asks you to explain every possible experiment using only statements such as 3 stones are red, 4 are blue, and 3 are green. As long as every measurement merely reveals a color that was already there, ordinary probabilities work beautifully. But now imagine a strange bag whose answers depend on which compatible set of questions you choose to ask, while different possible descriptions can also interfere with one another. You might discover that no list of hidden stones can reproduce every observed pattern. One option would be to give up describing the bag altogether. Another is to enlarge the bookkeeping system and allow weights that ordinary probability forbids. Negative quasi-probabilities perform something like that second job. They let physicists preserve enough information to calculate everything correctly, even when the underlying quantum state cannot be interpreted as a simple lottery over ordinary hidden possibilities. Scientists can reconstruct these quasi-probability landscapes experimentally by making many carefully chosen measurements on identically prepared systems. They never measure -5% directly. Instead, they gather ordinary detector results and use those results to rebuild the quantum distribution. When the reconstruction contains negative regions beyond what experimental errors can explain, those regions reveal something about the state that a purely classical statistical mixture would not possess. This has been demonstrated in systems ranging from individual light particles to trapped electromagnetic fields and other controlled quantum platforms. There is even a beautiful reversal hiding inside the idea. Probability was invented to describe uncertainty. You do not know which card will be drawn, so you assign chances to the possibilities. Quantum quasi-probability shows that sometimes uncertainty is not the whole problem. You can know everything quantum mechanics allows you to know about a system and still be unable to replace its description with ordinary positive probabilities for every imagined underlying property. The negative number, therefore, does not represent greater ignorance. In many cases, it represents the failure of the classical picture itself. That is a very different kind of mystery. When you do not know which toy is inside a closed box, the toy still seems perfectly definite, and your uncertainty belongs to you. Quantum negativity points towards situations where treating reality as a collection of definite but hidden classical answers simply does not reproduce what experiments allow. And perhaps that is why a number smaller than 0 can carry such an unexpectedly deep message. Nature is not asking you to believe in impossible chances. It is revealing the limits of the language you normally use to describe chances. The final experiments remain sensible. Detectors click ordinary numbers of times. Probabilities remain between impossible and certain. Nothing happens -3 times, but behind those perfectly normal results, the mathematical map may need regions below 0 to preserve the relationships that make quantum predictions work. You began with a rule that seemed unquestionable. Chances cannot be negative. You end somewhere more careful. Real experimental chances cannot be negative. But the deeper bookkeeping used to represent quantum possibilities sometimes can. And when it does, that negative sign is not nonsense hiding inside the equations. It can be a quiet fingerprint left by a world that refuses to behave as though everything unknown is merely something definite that you have not discovered yet. Weak values. Outside reality's normal limits. A quantum measurement can return 100 when every allowed answer is between 0 and 1. A measuring device can sometimes point to 100 even when the thing you are measuring has only two allowed answers, 0 and 1, and the machine does not have to be broken. This is one of the strangest features of a technique called weak measurement, where quantum physics allows an unusual number, known as a weak value, to appear far outside the ordinary range of a property. To see why that is surprising, imagine a tiny switch that can normally give only two answers, no or yes. If you measure it strongly, you expect 0 for no or 1 for yes and nothing else. You would never expect 12, 50 or 100 because those are not possible outcomes of the switch itself. Yet quantum experiments can be arranged so that a very gentle measurement of such a two-answer property produces an average pointer shift corresponding to a weak value of 100. The first thing to understand is what this does not mean. No single particle has suddenly acquired 100 units of a property whose physical outcomes stop at 1. A strong measurement performed on that particle would still return only one of the allowed ordinary results. The strange number appears because weak measurement asks a different kind of question. Instead of forcing the quantum system to give up a sharp answer immediately, the measuring device touches it so lightly that the information gained from one trial is almost useless. The pointer barely moves, and random noise can be larger than the signal. But scientists repeat the experiment many times with systems prepared in the same initial condition. Then they keep only a carefully chosen group of runs that end in a particular final condition. This combination of preparing the system one way at the beginning and selecting it another way at the end is called pre-selection and post-selection. The remarkable number emerges from the relationship between those two choices. Imagine sending thousands of tiny travelers into a maze. You give all of them the same starting instructions, barely touch each traveler as they pass one checkpoint, and at the exit, you keep only the rare travelers who leave through one very specific door. When you examine the tiny marks left at the checkpoint by just that selected group, their average can be enormously larger than you would have expected from any ordinary traveler. Quantum mechanics allows exactly this kind of amplification because the different possibilities contributing to the selected result can interfere with one another. Most of their contributions may nearly cancel, leaving a very small chance of reaching the chosen final state, while the tiny measurement signal does not cancel in quite the same way. Dividing one small quantity by another, even smaller one, can make the resulting weak value enormous. That is how a property whose strong outcomes are only 0 and 1 can be associated with a weak value such as 100. The number is therefore not a secret third measurement result hiding between 0 and 1. It describes how the weakly coupled measuring pointer behaves for a particular pre-selected and post-selected ensemble. This distinction is essential because the phrase "a measurement returned 100" can sound much more magical than the experiment really is. If you strongly measure the property in the usual way, you will never collect a single event labeled 100. Instead, you perform many extremely gentle interactions, sort the results according to the final selection, and discover that the average shift of the measuring device behaves as though it had responded to a value far beyond the normal spectrum. These are called anomalous weak values. They can even be negative when all ordinary outcomes are positive, or become extremely large when the initial and final quantum states are chosen to be almost incompatible. And although that sounds like a mathematical curiosity, weak values have practical uses. Because an anomalous weak value can magnify a tiny shift in the pointer, researchers have explored weak value amplification for detecting extremely small changes in quantities such as beam position, angle, frequency, or phase. Under the right experimental conditions, a microscopic effect that would otherwise be difficult to see can become easier to distinguish from certain kinds of technical noise. But weak value amplification is not a free magnifying glass that beats every measurement limit. The dramatic amplification comes at a price. The final state producing the largest weak values is often rare, so scientists throw away most of the experimental runs during post-selection. When all resources and all kinds of noise are counted, ordinary measurement strategies can sometimes perform just as well or better. That is why the most interesting part of weak values is not simply that they make measurements larger. It is what they reveal about how quantum information can be distributed between preparation, gentle interaction, and final selection. There is also an active debate about how literally weak values should be interpreted. One tempting story says that the weak value tells you what the quantum property really was between the first and final measurements. In simple cases, that language can be useful, but it can also mislead. If a two-valued property produces a weak value of 100, treating 100 as an ordinary hidden property would immediately create nonsense. Many physicists instead regard the weak value as a precise statistical quantity describing the response of a weakly probed pre- and post-selected quantum system. Different interpretations of quantum mechanics may tell different stories about what, if anything, existed in between. The experiment itself does not require you to believe that a particle secretly carried an impossible value. What is experimentally meaningful is the pattern in the pointer shifts and how accurately quantum theory predicts it. And this is where the idea becomes deeper than a strange number on a screen. In ordinary life, you assume the result of measuring something should belong entirely to the thing being measured. A ruler tells you the length of the table. A scale tells you the weight of the fruit. The answer seems to sit inside the object, waiting for the instrument to reveal it. Weak measurements show that quantum experiments can be more relational than that. The number you obtain can depend not only on how the system began, but also on which final group you later choose to examine, and on how gently you allowed the measuring device to interact with it in between. The measurement outcome is not always best imagined as a label peeled off the particle. It can be a property of the entire experimental arrangement. That is why 100 can appear where only 0 and 1 seem permitted without physics contradicting itself. The strong outcomes remain 0 and 1. The weak value belongs to a different question. And once you see that distinction, the paradox becomes more instructive than impossible. Quantum mechanics is not telling you that 1 is secretly equal to 100. It is showing you that there are ways of asking nature about a system that cannot be translated into the simple language of what value did the object possess. Sometimes the answer describes how possibilities from the beginning and the end combine through a measurement so gentle that no single trial can tell the story. You start with a switch that seems capable of saying only no or yes, and you end with a pointer behaving as though nature whispered 100. The strange part is not that arithmetic failed. The strange part is that you assumed every measurement had to be the same kind of question. The quantum pigeonhole principle can fail even without particles touching. Two particles can behave as though they have answered a question about each other even when they never collide, never exchange a little message, and never need to occupy the same point in space. And this is where the quantum pigeonhole effect becomes far stranger than a puzzle about counting. You already know the basic surprise. With 3 quantum particles and only 2 possible boxes, certain carefully prepared and carefully selected experiments can make every tested pair behave as though the 2 members of that pair were in different boxes. But now remove the most obvious explanation. Suppose the particles are kept apart. They do not bump into one another. There is no tiny collision that secretly pushes one particle away from another. If they still produce the unusual pigeonhole pattern, then whatever is happening cannot be explained by saying, they touched, so they changed each other. This is exactly why physicists became interested in versions of the effect built from non-local measurements. The word non-local can sound mysterious, but the basic idea is gentle. Instead of asking where particle 1 is and then separately asking where particle 2 is, the experiment can ask a question about their relationship, such as, are these 2 in the same kind of path or in different kinds of paths? Without revealing the complete individual answer for either particle, imagine 2 children each holding a card in different rooms. You do not ask either child whether the card is red or blue. You only build a procedure that tells you whether their colors match. The answer same or different contains information about the pair without telling you either card's color. Quantum experiments can perform an analogous kind of relationship measurement on particles that remain physically separated. In optical versions, the pigeons can be individual photons, and the boxes can be 2 possible polarization states, or two possible directions through carefully built interferometers. A photon may travel clockwise or counterclockwise through its own device, for example, while another photon travels through another path. Researchers can then probe whether a chosen pair belongs to the same category without requiring those two photons to crash into each other. Experiments and theoretical constructions have shown that the correlations needed for the quantum pigeonhole effect can indeed be generated without direct particle-particle interactions. This is important because an ordinary explanation based on repulsion immediately loses its power. If three charged balls were placed in two narrow channels, you might imagine that two entering the same channel push each other apart and create some strange final pattern. But separated photons do not need such a story. Their unusual behavior can arise from the quantum state, the way the pairwise question is measured, and the condition used to select the final results. The measurement itself becomes part of the physics. That does not mean a human mind magically changes the particles. A detector, an optical circuit, or another physical measuring system interacts with the quantum information in a controlled way, and that interaction can create correlations between particles that were independent before the measurement. This is called measurement-induced entanglement. It is one of the most useful lessons hidden inside the pigeonhole experiment. Measurements do not always behave like cameras that merely photograph something already completed. Some measurements can help create the very relationships they reveal. Imagine three bells sitting in separate rooms. Instead of listening to each bell individually, you have a strange device that can only answer whether two chosen bells have matching tones. The first comparison changes what can be said about later comparisons, because the act of learning the relationship also changes the combined state of the bells. Quantum pair measurements can behave in an analogous way. This is why you must be extremely careful with the sentence, "No two particles shared a box." It sounds as though scientists photographed all three particles at one instant and saw an impossible arrangement. That is not what happens. You cannot safely collect every pairwise answer and paste them together into one ordinary picture as though nothing changed between the questions. Different measurements may disturb or correlate the system, and strong measurements can destroy the conditions that allow the effect to appear. Experiments exploring different measurement strengths have found exactly this transition. The pigeonhole-like behavior can appear in the appropriate measurement regime, and then change as the measurement becomes stronger, and its back action becomes more important. So the real mystery is not that mathematics suddenly forgot how to count. Three ordinary objects placed into two ordinary containers still obey the ordinary pigeonhole principle perfectly. The quantum effect exposes something different. Pairwise statements obtained from specially prepared, post-selected quantum systems do not always behave like pieces of one hidden classical inventory. You cannot necessarily imagine a secret sheet of paper saying particle 1 was definitely here, particle 2 was definitely there, and particle 3 was definitely somewhere else, with every later measurement merely revealing entries already written on that sheet. The relationships can depend on the complete quantum experiment. This is also why physicists have debated how strongly the effect should be described as a genuine violation of the pigeonhole principle. Some analyses emphasize that the observed pairwise correlations are real and profoundly non-classical, while others point out that if you demand one complete simultaneous assignment for all three particles, ordinary counting has never literally disappeared. The paradox comes from trying to combine answers obtained under quantum conditions as though they were ordinary facts that all existed together beforehand. That disagreement actually teaches you more than the dramatic slogan does. It tells you exactly where common sense slips. You are used to thinking that if two things never touch, then nothing about one should matter to a measurement involving the other, unless a signal passes between them. Quantum physics gives you another possibility. A shared measurement can create or reveal correlations belonging to the pair as a whole, even when the individual particles never directly collide. No invisible force needs to leap between them. No faster-than-light message needs to be sent. No pigeon has to teleport from one box to another. The strange part lives in the structure of the joint quantum state. and in what the experiment is allowed to ask about it. And this opens a much deeper question than which box contained which particle. Perhaps some properties of a quantum system are simply not best understood as possessions carried privately by individual objects. Same and different can sometimes be meaningful properties of a relationship before there is any useful classical story about what each member of the pair was doing alone. That possibility matters far beyond pigeonhole puzzles, because modern quantum technologies often work by controlling relationships rather than treating every particle as an independent little object. Quantum error correction, distributed quantum information, entanglement generation, and many advanced measurement protocols all depend on the fact that information can live in correlations. A single part may tell you almost nothing, while the relationship among several parts carries the useful structure. So when the quantum pigeonhole effect survives without particles directly touching, nature is not showing you magical birds refusing to share a nest. It is showing you something quieter and more important. Interaction is not always synonymous with collision. Measurement is not always passive observation, and the most meaningful information about several quantum objects may live between them rather than inside any one of them. You began with 3 separate particles and 2 possible boxes, expecting the answer to be determined by where each particle individually went. But by the end, the deeper question is no longer where each particle was. It is whether where each one was ever enough information to explain the experiment in the first place. Counterfactual communication, information, may be transferred, even when the carrier never travels, between sender and receiver. Imagine receiving a message from someone across a sealed hallway, while every successful attempt seems to say that the messenger never crossed the hallway at all. That sounds like a contradiction, because communication normally means something travels. Sound moves through air, radio waves cross space, electrical signals move through wires, and light travels through fiber. Yet quantum physics contains a family of experiments called counterfactual communication that asks whether information can sometimes be learned from a distant choice, even in successful events where the particle used to probe that choice is not found traveling through the communication channel. The easiest doorway into the idea comes from an older quantum trick called interaction-free measurement. Picture a photon, a single packet of light, approaching a device that gives it 2 possible paths. The paths later come together again. When both paths are open and the device is adjusted correctly, the 2 possibilities combine so precisely that one detector never clicks. Now place an object in one path. The object changes the possible routes available to the photon, disturbing the delicate interference. Suddenly the detector that was supposed to remain dark can click. When that particular click occurs, you have learned that something blocked the distant path. Yet in that successful run, the photon could not have struck the object, because if it had been absorbed there, it would never have reached your detector. You discovered an object partly through an interaction that did not occur. Counterfactual communication takes that strange logic and turns the presence or absence of the obstruction into a message. Imagine Alice controlling the photon source and detectors while Bob is far away at the other end of an optical channel. Bob can choose whether to block a particular path. One choice can represent 0 and the other one. Alice sends photons into a carefully arranged network of mirrors and beam splitters and watches which detector responds. Bob never needs to send Alice a photon of his own. Instead, his choice changes the structure of the possible paths available to Alice's photon, and that change alters the pattern Alice can observe. More advanced proposals use long chains of these tiny choices together with something called the quantum Zeno effect. The name comes from a curious feature of quantum systems. Repeatedly checking whether a system has changed can strongly suppress the change itself. It is a little like repeatedly asking a child standing at a doorway, "Are you still here?" so often that the game is arranged to keep the child from leaving, except that the real quantum effect is about repeated physical interactions, not human attention. In counterfactual communication schemes, repeated stages, can make the probability of a photon entering Bob's transmission channel extremely small, while still allowing Bob's decision to affect what Alice finally detects. In an idealized limit, some protocols describe the successful information transfer as occurring without the photon carrying the message physically traveling from Alice to Bob and back. This is where the famous question appears. If the photon did not carry the message through the channel, what did? The safest answer is not nothing. The optical connection still matters enormously. Remove the possible channel, rearrange the mirrors, or prevent the quantum alternatives from being maintained, and the protocol stops working. The message is encoded in how Bob's distant choice changes the possibilities available to the entire experimental system. A path can matter even in a successful event where the detected photon is not said to have traveled down that path. This is one of the deepest differences between a quantum possibility and an ordinary unused road. If you stay home instead of visiting a shop, the road to the shop usually plays no role in what happens inside your kitchen. But in an interferometer, an available route can influence the final result because quantum alternatives can combine even when the final detected event cannot be described as a tiny ball simply traveling along every available path. There is, however, an important scientific dispute hiding behind the beautiful phrase, communication without particles. Physicists do not all agree on what should count as proof that a photon was truly absent from the channel. One test asks whether a weak interaction placed in the channel would leave a detectable trace. Analyses of some early counterfactual communication proposals found that photons associated with successful detections could leave such weak traces, leading critics to argue that calling the communication fully counterfactual was misleading. Modified protocols have been designed specifically to eliminate those traces, and experiments have demonstrated schemes in which successful detected photons leave no first-order weak trace in the communication channel under the chosen criterion. Yet researchers continue to debate whether every bit value, every discarded event, and every photon required to operate a real apparatus should count when deciding whether the complete communication process deserves the word counterfactual. That disagreement is important because the headline can otherwise become much more dramatic than the evidence. Counterfactual communication does not mean information teleports through absolute nothingness. It does not allow Alice to communicate faster than light. Bob cannot change his choice now and make Alice know it before any physically allowed influence could connect their laboratories. The protocol still depends on a physical experimental arrangement extending between the two sides. And building practical versions requires photons, optical components, careful timing, stabilization, and many repeated trials. Some photons may also be lost or discarded depending on the implementation. What is unusual is much narrower and more beautiful. In certain successful quantum events, Alice can infer something about Bob's distant action, even though the particle detected by Alice need not have visited Bob in the ordinary sense expected of a messenger. The information comes from how Bob changes what could have happened. That sentence sounds philosophical, but the laboratory mechanism is concrete. Bob blocks or opens a possible route. His decision changes interference conditions. Those change conditions alter the probabilities of Alice's detector clicks. Alice gathers those clicks and learns his bit. The path does not need to behave like a postal road with a tiny letter physically riding along it in every successful trial. Instead, the existence of the possible route becomes part of the communication resource. And that gives you a strange new way to think about information itself. You normally picture information as cargo. A letter contains words, a radio wave carries a signal, a flash of light brings a code. Counterfactual communication suggests that quantum information protocols can sometimes work more like a question whose answer depends on which possibilities remain open. What did not happen can become experimentally informative. A photon that was not absorbed can tell you an absorber was there. A route that the successfully detected photon did not traverse can still matter to the final statistics. An avoided interaction can leave enough structure for a distant decision to be inferred. That does not make absence into a magical substance. It means quantum experiments can extract information from the difference between possible evolutions including possibilities that never become the final detected event. Perhaps that is why counterfactual communication feels so difficult to place inside ordinary intuition. You began with the obvious belief that every message needs a messenger that crosses the distance carrying it. Quantum physics does not simply say that belief is false. It replaces it with a more careful question. Must the particle that finally tells you the answer have physically visited the place where the answer was chosen? Under certain definitions and carefully engineered conditions, quantum mechanics allows the answer to approach no, and in that small space between a channel must matter and a detected carrier must cross it, information begins to look less like an object moving through the world, and more like a pattern hidden in the possibilities the world was allowed to have. Counterfactual computation. A computer can reveal an answer, even along a branch where it never actually ran. A computer answers a question on a run in which its own power switch was never turned on, and quantum physics contains carefully designed experiments in which that sentence can be given a precise meaning. The idea is called counterfactual computation, and it begins with a very ordinary kind of problem. Imagine you have a machine programmed to answer a yes or no question, but you do not know which answer it will produce. Normally, there is only one sensible way to find out. You switch the machine on, let it perform the calculation, and read the result. Counterfactual computation asks whether quantum mechanics can sometimes let you discover that result while selecting an experimental outcome in which the computer itself did not perform the calculation. To understand how this can happen, forget the picture of a laptop sitting mysteriously unplugged while numbers appear on its screen. The computer in these experiments is a controlled physical process, and another quantum system determines whether that process is activated. That control can be prepared so that the experiment contains a possibility in which the computer runs and another possibility in which it does not. Those possibilities are kept coherent, meaning they are allowed to influence one another before the experiment finishes. This is the crucial ingredient. If you simply flipped a coin and sometimes switched a normal computer on and sometimes left it off, an off computer could obviously tell you nothing about the answer. In the quantum experiment, however, the possibility that the machine could have run changes the pattern of possible final outcomes, even in a selected outcome associated with the machine not running. You can think of it as setting up a maze whose exit depends on what a hidden machine would do if a traveler entered a particular passage. The traveler is allowed to follow quantum alternatives rather than one ordinary route, and at the end, those alternatives are recombined. Certain detector results can occur only if the hidden computer would produce one particular answer. When one of those results appears, you can infer the answer, even though the successful history used to identify that answer contains no execution of the computer. This does not mean that the answer appeared from nowhere. The working computer had to exist as a genuine physical possibility. Its behavior had to be built into the experiment. If you replaced it with a different machine that produced the opposite answer, the final pattern would change. What matters is the difference between actually carrying out a computation in the selected history and having the possibility of that computation influence a quantum experiment. Early theoretical work by Graham Mitchison and Richard Josser showed that this strange idea is allowed by quantum mechanics for decision problems, where a computer has two possible outputs. It also revealed an important limitation that prevents the story from becoming magical. Under their strict definition of counterfactual computation, you cannot simply design one perfect machine that learns both possible answers with certainty while guaranteeing that the computer never ran. The probabilities for obtaining the two answers counterfactually are constrained. In other words, quantum mechanics gives you something surprising, but it does not give you unlimited information for free. Later researchers developed more elaborate schemes using repeated quantum control, particularly techniques related to the quantum Zeno effect, in which a system is gently checked again and again in a way that can prevent a transition from completing. Here, the repeated structure can make one unwanted route less and less likely, while preserving information about what would have happened had the computer been allowed to operate normally. In 2006, researchers built an optical experiment demonstrating counterfactual quantum computation and used the idea with an implementation related to Grover's search algorithm. In their setup, light and optical components played the roles of the quantum control and computing process, and carefully arranged repeated stages greatly increased the probability of identifying the desired result counterfactually. This experiment helped turn what sounded like a philosophical puzzle into laboratory physics, but it also started an important debate about what the word counterfactual should really mean. Some physicists argued that certain protocols are genuinely counterfactual only for one possible output and not the other. If the answer happens to be one value, you can point to the successful history and reasonably say that the computer did not run. For another value, however, the full quantum evolution may contain contributions associated with the computer operating, making the claim much harder to defend. Lev Vaidman analyzed this issue and argued that proposed schemes could not be regarded as counterfactual for all possible outcomes under a strict history-based interpretation. The researchers behind the optical experiment responded that a broader physical definition captures what their protocol is doing. The disagreement remains useful because it prevents you from leaving with the false impression that quantum physics has discovered a universal machine that solves calculations without computing anything. The more accurate picture is stranger in a quieter way. Quantum mechanics allows the distinction between the computer ran and the computer did not run to participate in a larger interference experiment. A particular final detector result can sometimes tell you what the output must have been, while corresponding to a history in which the computing operation was not activated. That is very different from saying the calculation never mattered. In fact, the potential calculation matters completely. Remove the computer, change its program, or alter the output it would produce, and you change what can be inferred. The information is hidden in the structure of alternatives rather than being generated by an idle machine. There is also no violation of the cost of computation in the ordinary engineering sense. You still need an experimental apparatus. You still prepare quantum systems, control them with extreme precision, repeat trials, discard unsuccessful outcomes, operate detectors, and spend energy maintaining the laboratory. Counterfactual computation does not promise a laptop that performs enormous calculations while consuming nothing, nor does it mean you can ask a computer a question whose answer it could never calculate and somehow receive the answer anyway. The possible running branch must correspond to a real computation capable of producing the result. The strange advantage comes from arranging the experiment so that some successful outcomes reveal information without that computation being executed along the particular history associated with those outcomes. And this is where the subject begins to challenge something deeper than computing. You normally believe information must come from an event that actually happened. If you know a calculator says 7, you assume the calculator performed the steps that produced 7. If you know what is inside a box, you assume you looked inside or received information from someone who did. Counterfactual computation shows that quantum theory can make the boundary between what happened and what could have happened surprisingly important to what you can learn. A physical possibility can affect which final outcomes are available, even when the successful outcome you keep is associated with avoiding that possibility. But you should resist turning this into the claim that unreal events somehow possess magical power. Quantum alternatives are not imaginary stories in a human mind. They are parts of a mathematical and physical setup whose interference produces measurable statistics. The computer must be there. The option to run it must be physically meaningful. The experiment must preserve the delicate quantum relationships connecting the alternatives. Once those relationships are destroyed, the strange advantage disappears and you return to the ordinary rule. If you want the answer, run the machine. Perhaps that is the most revealing lesson of counterfactual computation. Classical thinking divides the world cleanly into what happened and what did not happen, then assigns information only to the first category. Quantum experiments sometimes refuse to keep that wall so simple. Under carefully controlled conditions, a path not taken can help determine which destination appears, and a calculation not executed along a selected branch can still help you infer what its answer would have been. The computer has not cheated logic. and you have not received knowledge from nothing. Instead, you have discovered that in the quantum world, the possibilities surrounding an event can become part of the physical machinery that tells you what is true. Quantum energy teleportation. Energy can be extracted somewhere using information from somewhere else. A battery that has never been charged should not suddenly let you take energy from it. Yet quantum physics contains a carefully tested protocol in which energy can be extracted from one place after a measurement is made somewhere else, and the measurement result is sent across as ordinary information. This is called quantum energy teleportation, or QET, and despite the dramatic name, no packet of energy vanishes from one laboratory and instantly appears in another. The real mechanism is stranger and more precise. Start with two small parts of a quantum system, one near Alice and one near Bob, separated from each other but sharing quantum correlations. The whole system can be prepared in its ground state, which simply means its lowest possible total energy state. At first, this sounds like the worst possible place to search for usable energy. If the system is already as low as it can go, where could any extra energy possibly come from? The answer begins with an important detail. The whole system can be at its lowest total energy, while its different regions still contain correlations that connect what can happen in one place with what can happen in another. Alice performs a local measurement on her part of the system. Making that measurement is not free. Her measuring device interacts with the system and injects energy into it. So QET does not create energy from nothing. Energy conservation remains completely safe. But Alice gains something else during the measurement. Information about the quantum fluctuations and correlations in the shared state. She then sends the result of her measurement to Bob through an ordinary classical channel. Perhaps something as simple in principle as a conventional electronic signal. Bob waits for that information. Once he receives it, he chooses a very specific local action on his part of the quantum system, with the action depending on the result Alice obtained. If he performs the correct operation, Bob can extract positive energy from his local region. That is the part that earns the process its extraordinary name. The energy Bob extracts can become available before the physical disturbance created by Alice has had enough time to travel through the material itself and reach him in the ordinary way. Imagine, for example, a long chain of tiny quantum components. Alice touches the left end and makes her measurement. Normally, you might expect any energy she added there to spread step by step through the chain until some of it eventually arrived at Bob on the right. QET allows a different sequence. Alice measures the left side, sends Bob the measurement result by a faster classical communication route, and Bob uses that information to extract energy locally on his side before the ordinary energy-carrying excitations from Alice's disturbance have crossed the chain. This can sound as though energy has jumped across empty space, but that is not the correct picture. Bob's operation is exploiting correlations that were already present in the shared quantum state. Alice's measurement tells Bob which local action will work. Without that message, Bob does not know the correct operation, and simply guessing will not let him reliably extract the same energy. So the classical information is essential. Because Alice's message cannot travel faster than light, QET cannot be used for faster than light communication and does not break relativity. Bob cannot extract the useful energy before the information needed to choose his operation reaches him. Another puzzle immediately appears. If the system began in its lowest possible total energy state and Bob removes energy from his region, does his part somehow fall below the ground state? Locally, something resembling that can happen in the energy bookkeeping. Quantum systems can have local regions whose energy contribution becomes lower than the ordinary ground state reference after Bob's operation, while the total energy of the complete system still remains perfectly physical and respects the lower bound. You can think of the total energy as belonging to the whole connected quantum system, rather than as a pile of independent coins permanently assigned to separate locations. Alice's measurement injects energy into the full system. The measurement information then allows Bob to perform an operation that changes the local energy balance and releases some usable energy at his end. The accounting across the complete protocol always balances. Nothing is produced for free. In fact, the amount Bob can extract is generally smaller than the energy Alice had to inject during her measurement. So, QET is not a perpetual motion machine, a secret battery, or a way to defeat thermodynamics. Its importance lies somewhere else. It shows that quantum correlations can determine where energy becomes locally accessible. That difference between energy existing somewhere in a total system and energy being locally extractable is easy to overlook. Suppose Bob has a locked box containing a mechanism, but he does not know which of two buttons will safely release its spring. Alice learns which button is correct and sends him one bit of information. The information itself does not contain the mechanical energy stored in the spring, yet receiving it changes Bob's ability to extract that energy. QET has a distant resemblance to this, except the resource is not an ordinary hidden spring. The crucial structure comes from quantum correlations in the shared state, and Alice's measurement changes the system in a way that makes her information useful for Bob's energy extraction. This is why saying energy travels inside the message is wrong. The classical message can be only a few bits. Those bits tell Bob how to act. They are not carrying the energy he later collects. Researchers have proposed QET in systems such as chains of interacting quantum particles, quantum fields, and trapped ions, and laboratory demonstrations have implemented the essential protocol using controllable quantum platforms. The amounts involved are extremely tiny. Nobody is teleporting enough energy to power a lamp, charge a phone, or run a spacecraft. Current experiments are about understanding quantum information and quantum thermodynamics at their most basic level. But tiny does not mean unimportant. The experiments test an unexpected relationship between knowledge and usable energy. In classical physics, information can obviously help you use energy more intelligently. You need to know where fuel is before you can burn it. But QET makes this connection part of the microscopic physics itself. The measurement result changes which operation can draw energy from Bob's local region. This also explains why quantum entanglement is important, but should not be treated like a mysterious tunnel carrying power. Entanglement creates correlations between distant parts of the system, but entanglement alone cannot tell Bob what Alice measured. The ordinary message must still arrive. Nor does Alice's measurement secretly command Bob's system to release energy instantly. Before the message reaches him, Bob cannot know which operation will succeed. The protocol therefore combines three ingredients that each play a different role. Shared quantum correlations prepare the resource, Alice's local measurement gathers information while injecting energy, and classical communication tells Bob how to perform the local operation that extracts energy. Remove any one of those ingredients, and the useful effect disappears. That is what makes QT so different from the fictional teleportation you see in movies. Nothing is dematerialized. Nothing is reconstructed from a beam. There is no glowing parcel of energy crossing space invisibly. Instead, the protocol reveals that energy and information are more tightly connected in quantum systems than everyday intuition suggests. A distant region can possess no immediately accessible energy for Bob under one set of conditions and then become capable of giving up energy after Bob learns the right piece of information about a correlated region elsewhere. The physical system was there all along. The correlations were there all along. What changed was Bob's ability to use them. And perhaps that is the most interesting question QET leaves behind. When you say that energy is located somewhere, you imagine it sitting there like water in a cup, waiting to be carried away. Quantum physics suggests that this picture can be too simple. In some systems, what matters is not only how much total energy exists, but also what information is available, how different regions are correlated, and which local operations can turn those correlations into useful work. Quantum energy teleportation does not move energy faster than light, does not create energy from nothing, and does not give you a free source of power. What it does is more subtle. It shows that knowing something about one part of a quantum system can change what you are physically able to extract from another. And once information itself becomes part of the route to usable energy, the line between where the energy is and where the energy can be accessed becomes far less obvious than the world around you ever taught you to expect. The quantum vacuum can give energy back before it seems to take it. Empty space can briefly behave as though it owes you energy, pays part of the debt first, and only later reveals where the bill came from. But this does not mean the vacuum is a hidden battery or that energy conservation has failed. The strange idea comes from quantum field theory, where what you call empty space is not the same thing as absolute nothingness. Even when no ordinary particles are present, quantum fields still exist, and their lowest energy state is called the vacuum. Normally, you might imagine that the lowest possible energy means every tiny region of space must always contain exactly zero usable energy. But quantum fields are more subtle. In certain specially prepared states, the energy density measured in one small place for a short time can be lower than the ordinary vacuum level. Physicists call this negative energy density. The word negative sounds dangerous because it seems to suggest that nature has somehow created less than nothing, but that is not the right picture. The 0 point used here is a reference associated with the vacuum state. So negative energy means a local measurement can fall below that reference level. It does not mean a container holds a pile of minus energy coins that you can collect forever. Real examples of related effects appear in quantum field theory around carefully arranged boundaries and in specially prepared states of light known as squeeze states, where the usual vacuum fluctuations can be reduced in one aspect while becoming larger somewhere else. The remarkable part is that quantum theory does not simply forbid negative energy. Instead, it allows it under strict conditions. Imagine standing beside a river where the normal water level is marked by a line on a wall. For a moment, the surface might dip below the line, but if you watched long enough, you would discover that the missing water cannot simply remain missing forever. Quantum fields behave somewhat like that, except the restriction is far stronger and much more precise. Mathematical results called quantum energy inequalities limit how negative the energy can become and how long that negative region can last. A deep dip must be extremely brief. A longer lasting dip must be much smaller. Nature seems willing to let the local energy fall below the vacuum level, but it refuses to let you make the deficit arbitrarily large and permanent. This leads to an even stranger idea, sometimes nicknamed quantum interest. Suppose an observer encounters a short pulse of negative energy. In many studied quantum field models, that negative pulse cannot exist alone. It must be balanced by positive energy, and the compensation may need to be larger than the original negative amount. The farther apart the negative and positive pulses are allowed to become, the greater the required overpayment can be. It is as if nature permits a tiny energy loan, but charges interest for keeping the loan open. Yet the order is not always as simple as borrow first, repay later. In some theoretical arrangements, the positive pulse can occur before the negative one. From the point of view of someone watching the sequence, the field can appear to deliver extra positive energy and only afterward produce the negative energy region that makes the full pattern possible. This is the careful sense in which the vacuum can seem to give energy back before it takes it. Nothing has been sent backward through time. The later negative pulse has not reached into the past and changed the earlier positive one. Rather, the complete quantum state contains a pattern of energy density across time, and the allowed positive and negative parts are constrained together. You are trying to understand the pattern one moment at a time, while the mathematics describes the entire allowed structure. Think of looking at only a few frames from a wave passing across a rope. One frame may show the rope above its resting line, another below it. If you insist on treating each frame as a separate event with its own independent story, the sequence can look mysterious. But the crest and trough belong to one wave. In a similar way, positive and negative energy regions in a quantum field can be parts of one constrained state rather than independent packets making unrelated decisions. There is also an important reason these restrictions matter. If large amounts of negative energy could be created easily and kept around for as long as you wanted, many exotic ideas in theoretical physics would become much easier to build. Negative energy often appears in discussions of traversable wormholes, unusual space-time geometries, and hypothetical shortcuts through space because general relativity responds to energy in ways that could, in principle, produce very strange gravitational effects. But quantum energy inequalities make unlimited negative energy extraordinarily difficult. They do not automatically prove that every exotic spacetime idea is impossible, yet they place severe limits on the kind of negative energy distributions ordinary quantum fields can support. Nature seems to allow the loophole while simultaneously making the loophole tiny, and there is another misconception worth removing. The quantum vacuum is not constantly producing little particles that literally pop into existence, borrow energy for a short time, and then disappear before the universe notices. That popular picture can be useful as a cartoon in certain calculations, but taken literally, it is misleading. Energy conservation is not suspended for a short time just because quantum mechanics contains uncertainty. Modern quantum field theory conserves energy according to the symmetries of the system. Negative energy phenomena arise from the structure of quantum states and the way energy density is defined and measured, not from nature briefly forgetting its own rules. Even vacuum fluctuations should not be pictured as tiny batteries randomly handing out free energy. A detector placed in ordinary empty space cannot simply sit there harvesting unlimited power from the vacuum. If it could, empty space would become an endless fuel source, and every conservation law around you would quickly become useless. Instead, extracting or creating unusual quantum states requires physical resources, carefully controlled interactions, or special conditions. What makes the subject fascinating is that conservation survives even while the local story becomes unfamiliar. At one moment, a small region can register below the normal vacuum energy. Somewhere else or sometime nearby, positive energy restores the larger accounting. Sometimes the compensation follows. In suitable theoretical descriptions, it can proceed. Either way, the complete pattern remains tightly restricted. That is why the phrase, "the vacuum gives energy back before taking it," should not make you picture a cosmic bank transferring money from tomorrow into today. A better picture is that the quantum field does not treat every instant as an independent account. The allowed energy pattern is spread across time, and the positive and negative pieces are linked by rules that only become obvious when you look at more than one moment. Your everyday intuition was built from objects that carry positive energy, move forward, collide, heat up, and cool down. It expects energy to behave like a substance that can simply be stored in one place and counted. Quantum fields reveal that local energy can be stranger than that, while the total physical laws remain intact. A region can dip below the vacuum reference, another region can rise above it. The timing of those changes can challenge the simple story of taking first and returning later, but the universe never hands you a free lunch. The negative part is limited. The positive part cannot be ignored, and the longer you try to separate them, the more demanding the restrictions become. So the deepest surprise is not that the vacuum breaks the rules. It is almost the opposite. The vacuum is allowed to behave in ways that look impossible for a moment, precisely because deeper rules keep the entire pattern under control. What seems like energy arriving before the debt exists is really a reminder that in quantum field theory, a single instant may be too small a window through which to understand what the field is doing. Quantum backflow. A particle moving right can produce probability flowing left. Picture a river in which every drop of water is moving east, yet for a brief moment the amount of water on the western side increases. Nothing turns around, no hidden pump pushes the water backward, and still the flow appears to go the wrong way. A real river cannot do this, but a quantum particle can produce something surprisingly close to it, and physicists call the effect quantum backflow. The setup sounds almost too simple to be strange. Imagine a particle moving freely along a straight line. You prepare it so that every momentum component in its quantum state points to the right. In ordinary language, every contribution says the same thing. This particle is heading forward. Classical reasoning would then make an obvious prediction. If you draw an imaginary line in front of the particle and keep watching, the probability of finding the particle on the left side of that line should steadily decrease as time passes. After all, if everything is moving right, how could anything associated with the particle flow left? Quantum mechanics gives a different answer. For certain carefully shaped quantum states, the probability of finding the particle on the left side can temporarily increase, even though the state contains no left-moving momentum at all. The probability current, the quantity physicists use to describe how probability flows through space, can briefly point backward. That is quantum backflow. The most important word here is probability, because the effect does not mean a tiny marble races right while secretly sliding left at the same time. A quantum particle is not described by one classical trajectory before you measure it. Instead, its state can contain several right-moving wave components with different momenta. Each one individually points forward, but quantum waves do something that ordinary particles cannot. They interfere. Where different parts of the wave overlap, they can strengthen or weaken one another. Usually you hear about interference producing bright and dark patterns, but here interference changes the direction of the probability current itself. Two or more wave components can all be traveling toward the right, while their combination produces a local region in which probability flows toward the left. The strangeness is created not because any component carries negative momentum, but because the whole quantum state contains relationships between the components that cannot be understood by examining them one at a time. Think of two people walking east while holding opposite ends of a long, flexible rope. Both people continue east, but the shape of the rope between them can briefly move west as waves travel and overlap along it. The rope analogy is not perfect, because quantum probability is not a physical rope, but it gives you a hint. The behavior of the combined pattern does not have to copy the motion of each ingredient. Quantum backflow takes that idea much further. The quantity flowing backward is the probability associated with where a future position measurement may find the particle. That creates an immediate puzzle. If the particle has only positive momentum, should that not guarantee that any position measurement later will show a simple forward migration? No. Momentum and position are related in quantum mechanics, but they do not form the kind of one-to-one map you expect from a thrown ball. Knowing that every momentum contribution is positive does not supply a hidden path telling you exactly where the particle sits at every intermediate moment. The wave function evolves as a whole, and the interference inside that evolution can rearrange probability in ways that have no classical equivalent. This is why backflow is sometimes described as one of the cleanest demonstrations that positive momentum does not always imply positive probability current. Those two ideas are almost identical in classical physics, yet quantum mechanics quietly pulls them apart. There is another remarkable detail: the effect is limited. Quantum theory does not allow an arbitrarily large amount of probability to surge backward while all momentum remains forward. In the ideal one-dimensional problem, mathematicians found a universal upper limit of only about 4%. That may sound small, but the smallness makes the effect more interesting, not less. Nature permits the backward flow, yet constrains it with extraordinary precision. The limit does not depend on the particle's mass in the simple idealized case, and it does not disappear merely because you choose a faster particle. It seems to arise from the structure of quantum mechanics itself. In other words, backflow is not a trick caused by a particular kind of atom or a poorly designed measuring device. It is built into the mathematical relationship between quantum waves, momentum, and position. The phenomenon also leads directly into a surprisingly difficult question. When does a quantum particle actually arrive somewhere? For a classical car, arrival time is easy. You watch the car cross a line and note the clock. For a quantum particle, defining an exact arrival time distribution is much more subtle because the particle's state can spread, interfere, and even create backflow near the boundary you are using as your finish line. If probability can temporarily move away from the detector even when every momentum component heads toward it, then the particle is moving toward the detector is not enough to predict a simple stream of arrivals. This is one reason backflow has become useful in the study of quantum arrival times and transport. It exposes the danger of treating a quantum wave like a crowd of invisible classical particles, each carrying its own definite velocity and position. If that picture were correct, backflow would be impossible. A collection containing only right-moving particles could never increase its population on the left without some of them turning around. Quantum mechanics does not need them to turn around because it is the combined amplitude pattern that evolves. And there is an especially important distinction hidden here. Backflow does not violate conservation of probability. Probability is not appearing from nowhere. It is being redistributed. If one region gains some probability, another region loses the corresponding amount. Nor does backflow give you a way to send information backward in time, reverse cause and effect, or make a particle travel faster than light. The word backward refers only to the local direction of probability flow compared with the sign of the particle's momentum components. Nothing about the effect requires time itself to reverse. What it challenges is a simpler assumption. That direction must always belong to a quantum particle in the same way direction belongs to a moving stone. In the world you experience, velocity, motion, and flow seem almost interchangeable. If every car on a highway is driving east, traffic flows east. If every leaf on a stream drifts downstream, the collection of leaves moves downstream. Your intuition is built from millions of examples like these. So it quietly teaches you that the direction of the parts must determine the direction of the whole. Quantum backflow shows that interference can break that rule without breaking any physical law. Every momentum ingredient can say right, while the complete state briefly says left in the only language probability current knows how to speak. And perhaps that is what makes this small, almost hidden effect so revealing. It does not require a black hole, a cosmic distance, or an exotic new particle. You need only one quantum object moving freely, and one question that seems embarrassingly simple. If everything points right, can anything flow left? Classical physics answers immediately. Quantum mechanics waits, combines the waves, and quietly answers yes. Quantum superoscillation. A wave can locally oscillate faster than any frequency used to build it. Build a wave using nothing but slow ingredients, and a tiny part of that finished wave can somehow wiggle faster than every ingredient you put into it. That sounds like hiding a racing car inside a pile of bicycles, yet it is a genuine mathematical and physical phenomenon called superoscillation. The first important surprise is that superoscillation is not exclusively quantum. Ordinary light waves, sound-like wave systems, and mathematical signals can display it too. But because quantum particles are described by wave-like states, the same strange behavior can appear inside quantum mechanics and produce consequences that feel especially unsettling. To understand it without equations, imagine making a complicated wave by combining many simple waves. One rises and falls slowly, another rises and falls at a slightly different rate. You add dozens of them together, but you impose one strict rule. None of your ingredients is allowed to oscillate faster than a certain maximum frequency. Common sense suggests that the finished pattern cannot contain anything faster than that maximum. After all, where would the extra speed come from? Yet if the waves are given extremely precise strengths and alignments, their peaks and valleys can cancel in almost every place while reinforcing one another in one very small region. Inside that narrow region, the combined pattern can cross up and down astonishingly rapidly, more rapidly than the fastest individual wave used to construct it. This is a superoscillation, a band-limited wave locally behaving as though it contains a frequency that does not appear among its actual building blocks. The word locally is the key that prevents the phenomenon from becoming magic. The entire wave has not secretly acquired a new high-frequency ingredient. If you examine the complete signal and separate it into the ordinary frequencies from which it was constructed, every component still lies below the original limit. The extraordinary rapid oscillation exists only across a restricted region because the slower components have been arranged to interfere with almost unbelievable precision. It is similar to placing many large shadows on top of one another so that their edges create a tiny bright detail. The tiny detail does not mean you secretly added a smaller lamp. It emerged from the arrangement of the larger patterns. Superoscillation therefore teaches you something easy to miss about waves. The local appearance of a pattern does not always reveal the frequencies contained in the whole pattern. A small piece can look faster than anything used to build it, but nature makes you pay heavily for this trick. As the superoscillation becomes faster, sharper, or extends across a larger region, the useful part of the wave usually becomes extremely weak, while enormous features appear elsewhere. In optical superoscillation, for example, a very tiny central feature can be surrounded by much stronger sidebands that contain most of the energy. Making the tiny feature more extreme can demand a dramatic increase in those unwanted regions. So superoscillation does not let you create unlimited detail or unlimited energy from gentle waves for free. The faster local wiggle is purchased by carefully arranged cancellation and by moving much of the wave's strength outside the place you care about. Imagine whispering with 1,000 people arranged around a stadium so precisely that their voices nearly cancel everywhere except one tiny seat, where a complicated sound becomes sharply defined. The sharp sound at that seat might seem impossible if you only inspected the voices individually, but the price is that an enormous amount of coordinated activity is happening across the rest of the stadium. Quantum mechanics makes this idea even more interesting because the wave describing a particle is connected with the probabilities of what measurements may reveal. A quantum state can be built only from momentum-like components below a chosen limit and still possess a small region whose phase varies as though a much larger local momentum were present. If you probe that region in the appropriate way, the local behavior can therefore appear to exceed the range suggested by the state's ordinary components. This does not mean the particle has secretly gained forbidden energy. A normal measurement of the full momentum distribution still finds only the momenta that were genuinely used to construct the state. The surprisingly large local behavior belongs to the interference pattern, not to an extra hidden particle property. This difference matters because otherwise, superoscillation sounds like a loophole in conservation laws. It is not. Nothing moves faster than light simply because a wave superoscillates. No new energy appears. No high-frequency photon is created merely because a small region of a lower frequency field changes rapidly. The complete wave still obeys the same physical limits it had before. What changes is how misleading a tiny piece of that wave can look when separated from the enormous structure supporting it. And this strange ability has become useful outside foundational quantum questions. Light can be engineered into super oscillatory patterns containing features smaller than the size ordinary focusing intuition would suggest, allowing researchers to explore forms of far-field super-resolution imaging and extremely precise optical measurements. The principle works because carefully designed interference creates tiny features without requiring those exact tiny spatial frequencies to appear as ordinary propagating ingredients. Although the price again appears as strong surrounding regions, poor energy efficiency, or extreme sensitivity to imperfections. That sensitivity reveals another beautiful limitation. A superoscillation is not a robust little wave hiding inside the larger one. It is more like an extraordinarily delicate agreement among many waves. Change their strength slightly, shift their phases, introduce noise, or remove one important component, and the rapid local pattern can weaken or vanish. What looks simple in the tiny superoscillating region may require immense precision across the entire state. This turns the phenomenon into almost the opposite of what it first appears to be. At first you think nature has somehow smuggled a fast frequency into a slow wave. Look more closely and you discover that nothing was smuggled anywhere. The fast-looking region is created by a complicated conspiracy of slow waves, each doing something completely allowed, arranged so perfectly that their combined behavior temporarily imitates something none of them possesses alone. And that leaves you with a deeper lesson about what it means to analyze a system by looking only at one small piece. You are naturally tempted to see several rapid wiggles and conclude that a rapid ingredient must be hiding there. Most of the time, that intuition serves you well. Superoscillation proves that it is not a law. Sometimes an extreme local feature can emerge from completely ordinary ingredients because relationships between those ingredients matter more than any one ingredient by itself. The universe has not exceeded its own frequency limit. Your eyes have simply focused on the one region where countless slower possibilities have been arranged to imitate something faster. And perhaps that is the quiet wonder of superoscillation. Nature can create a pattern that seems to contain what was never put into it, not by breaking a limit, but by using interference so precisely that the limit becomes almost impossible to recognize from one small part of the whole. Quantum revival. A wave function can collapse into chaos and later reconstruct its earlier shape. A quantum wave can appear to lose its shape completely, spread into a complicated blur, and then much later rebuild something astonishingly close to the pattern it started with, almost as if the system remembered a picture everyone thought had been erased. This phenomenon is called a quantum revival, and the first thing to understand is that nothing literally dies and comes back to life. The wave function has not been destroyed and recreated from nowhere. Instead, many parts of the quantum state slowly drift out of step with one another, and then, under the right conditions, naturally come back into step again. Imagine a group of children running around a circular track. At the beginning, they all stand together at the starting line, forming one tight group. Then each child runs at a slightly different speed. After a while, they spread around the track until the original group seems completely lost. If you took a photograph at that moment, you might think there was no memory of the starting arrangement left at all. But suppose their speeds have very carefully related values. After enough laps, the faster runners gain whole laps on the slower ones, and eventually many of them can meet again near the starting position. Nobody reversed direction. Nobody received instructions to return. Their different motions simply accumulated in such a way that their relative positions lined up again. A quantum revival works through a similar idea, although what is evolving is not a collection of little runners, but the different energy components making up a wave function. When a quantum state is created, it can be formed from many allowed energy states at once. Each of those components develops its own phase as time passes, meaning you can think of each one as carrying an invisible internal rhythm. At first, those rhythms may be arranged so that they combine into a clear, localized wave packet. Then they gradually lose synchronization. One component gets ahead, another falls behind, and the original packet begins to spread. In some systems, the spreading can become so complicated that the probability distribution looks almost scrambled. Yet the underlying quantum evolution can remain perfectly orderly. The information about the original state has not necessarily vanished. It has been distributed among many relative phases that are difficult to recognize by looking at the wave directly. If the energy levels of the system have the right structure, those phases can later realign. When enough of them return to nearly their original relationships, the wave packet reforms. That moment is the revival. This can happen with atoms prepared in highly excited states, with molecules, with trapped particles, and with other quantum systems whose energy levels allow the necessary rephasing. One famous setting involves Rydberg atoms, atoms in which an electron has been lifted into a very high-energy orbit-like quantum state. Researchers can create a localized electron wave packet from several nearby energy levels. At first, the packet can move in a way that roughly resembles an electron traveling around the nucleus. Then the different energy components drift apart in phase, causing the packet to spread until the simple motion becomes difficult to recognize. Later, however, the phases can line up again, and the localized packet returns. What looked like irreversible decay was really hidden organization continuing underneath. This is why the word collapse in the title must be treated carefully. Quantum revival is not usually about wave function collapse caused by a measurement. It is about a wave packet collapsing or dispersing in the everyday sense of losing its localized shape. If a strong measurement actually destroyed the coherence between the relevant components, the clean revival could disappear. The phenomenon depends on the quantum state preserving enough coherence for its different pieces to remember their phase relationships. That gives quantum revival a very different meaning from simply reversing a movie. The system does not run backward through all its earlier configurations. During the time between the original packet and the revival, it can pass through extremely complicated states that do not look like the original one at all. The eventual reconstruction happens because the clocks hidden inside the different energy components line up again, not because time itself reverses. Even more interestingly, the wave function does not always wait for a complete revival. At certain earlier times, it can form fractional revivals, where several smaller copies of the original wave packet appear at different locations. Imagine the original group of runners returning not as one crowd, but as 2, 3, or 4 evenly spaced groups around the track. In quantum systems, this splitting can produce striking interference structures and multiple localized packets. These fractional revivals reveal that the apparently chaotic middle period contains a highly organized mathematical pattern. The wave is not merely dissolving, it is reorganizing itself through a sequence that can include partial reconstructions before the full pattern returns. There is an important limit, however. Perfect revivals require special relationships among the system's energy levels. In many real systems, those relationships are only approximate, so the returning wave packet may resemble the original without reproducing it exactly. Environmental noise can also disturb the phases. Collisions, stray electromagnetic fields, thermal motion, or interactions with surrounding particles can destroy coherence, making the revival weaker or eliminating it entirely. That fragility is why scientists often study the effect in highly controlled environments. A classical cloud of particles with genuinely random motions would not usually rebuild its original shape simply by waiting. Quantum revival is possible because the wave function carries phase information that remains hidden even when the visible probability pattern has become complicated. And this difference teaches you something important about what lost means in quantum physics. When a clear pattern disappears, your eyes naturally tell you that the information must have been destroyed. You watch perfume spread through a room and never expect it to gather itself back into the bottle. You watch ink dissolve in water and assume the original drop is gone forever. Those processes involve enormous numbers of particles and uncontrolled interactions, so recovering their microscopic arrangement is effectively impossible. A coherent quantum system can behave differently. Its apparent disorder can still be generated by a precise, reversible evolution, allowing information that looks inaccessible to return in recognizable form later. The revival is therefore not memory in the human sense. The particle does not know its past. There is no tiny record stored somewhere saying what shape to rebuild. The memory is contained in the continuing relationships among the components of the wave function. Their phases are the record. As long as those relationships survive, the system can carry the blueprint of its earlier shape through a period when that shape seems completely absent. And perhaps that is the most beautiful part of quantum revival. The universe can hide order so deeply inside complexity that disappearance and destruction become two very different things. A wave packet can spread until its beginning is almost impossible to see. Yet the structure needed to recover that beginning can still be quietly evolving inside it. Then, at the right time, the scattered rhythms meet again. The blur sharpens, and something that seemed lost returns. Not because nature remembered it, but because nature never completely forgot. The Loschmidt echo, quantum evolution, can appear to reverse toward a state that should have been lost. Scramble a quantum system until its original pattern seems hopelessly gone, then change the rules in just the right way, and part of that lost pattern can come rushing back toward you like an echo from a state the system was never expected to revisit. This is the idea behind the Loschmidt echo, a tool physicists use to ask a deceptively deep question. If quantum evolution is allowed to run forward for a while, and you then try to reverse it, how closely can the system return to where it began? The name comes from physicist Joseph Loschmidt, who challenged the old puzzle of irreversibility. The microscopic laws of physics often work in ways that can, in principle, be reversed. Yet the world around you clearly does not behave that way. A broken plate does not leap together. Warm coffee does not spontaneously separate its heat and become hot in one tiny region while the room cools. disorder seems to grow. Loschmidt wondered how an irreversible world could emerge from laws that seem so reversible underneath. The modern Loschmidt echo turns that philosophical problem into something scientists can actually measure. Imagine preparing a quantum system in a carefully known state. You let it evolve under one set of physical conditions for a certain amount of time. Its state becomes more complicated, spreading information through many degrees of freedom until the starting pattern becomes difficult to recognize. Then you attempt the reversal. You change the governing conditions so that, if everything were perfectly controllable, the system would retrace its quantum evolution back toward its beginning. Finally, you compare the returned state with the original one. The amount of similarity is the echo. A strong echo means the system came back very close to where it started. A weak echo means tiny imperfections during the attempted reversal grew large enough to prevent a good return. This makes the Loschmidt echo very different from a quantum revival. In a revival, the system is normally left to evolve under its own dynamics until different parts naturally come back into alignment. In a Loschmidt echo experiment, researchers actively try to reverse the evolution. It is less like waiting for runners to meet again after many laps, and more like suddenly blowing a whistle and asking every runner to retrace the exact path they just took. If their speeds and directions are reversed perfectly, the group could theoretically return to its starting arrangement. But now imagine that one runner's direction is wrong by the tiniest amount. At first, the error seems meaningless. After enough motion, however, that tiny mistake can grow into a large separation. The Loschmidt echo measures how badly those tiny imperfections damage the return. This is why the effect has become closely connected with the study of quantum chaos. In some systems, a microscopic change in the Hamiltonian, the set of physical rules controlling the evolution, can cause the returning state to lose similarity with the original remarkably quickly. You do not need the mathematics to understand what that means. The quantum system may be so sensitive to tiny imperfections that reversing almost everything correctly is still not enough. The echo fades because almost the same rules are not always the same rules. Scientists have observed Loschmidt echo-like behavior in nuclear magnetic resonance experiments, cold atoms, microwave systems, and other controllable quantum platforms. One especially intuitive version comes from spin echo techniques. Atomic nuclei or other quantum spins begin with a certain collective order. Their phases then spread apart because slightly different parts of the sample experience slightly different conditions. The organized signal weakens and seems to disappear. Apply the right sequence of pulses, however, and those phases can be redirected so that they come back together, producing an echo. The lost signal was not necessarily destroyed when it vanished from view. Much of the information remained hidden inside the relative phases of the microscopic components. The reversal pulse allowed that information to become visible again. But a true Loschmidt echo goes further than simply correcting known static differences. It asks how faithfully an entire quantum evolution can be undone when the backward evolution is not perfectly identical to the forward one. That distinction turns the echo into a microscope for irreversibility. If the echo falls rapidly, scientists learn that the system is highly sensitive to perturbations. If it survives for a long time, the evolution is more stable. And because real experiments can never reverse every interaction perfectly, the fading echo shows how information that is still present in principle can become practically unrecoverable. This is one of the most important lessons hiding inside the phenomenon. Lost can mean several very different things in physics. Information can be truly destroyed by interaction with an uncontrolled environment, but it can also become scrambled so thoroughly that recovering it requires absurdly precise control. Suppose you pour a box containing red and blue beads onto a table and mix them thoroughly. The colors are still there. No information about the individual beads has vanished. But restoring the exact original arrangement would require remembering where every bead came from and reversing every tiny movement. The quantum version is much more demanding because the information is stored not only in obvious positions, but also in delicate phase relationships and correlations. A tiny uncontrolled magnetic field, weak collision, stray vibration, or unnoticed coupling to the environment can alter those relationships. The farther the system evolves, the more places the error can spread. So when an echo returns, it is evidence that a surprising amount of microscopic information survived the apparent scrambling. When the echo dies, it tells you how rapidly that information becomes inaccessible under imperfect control. This has practical importance for quantum technologies. A quantum computer must preserve delicate states long enough to perform useful calculations. If tiny imperfections rapidly destroy the ability to reverse a quantum evolution, that system will be difficult to control. Loschmidt echoes can therefore help researchers study decoherence, error growth, many-body dynamics, and how information spreads through interacting quantum systems. They can reveal whether a disturbance remains local or spreads through the entire system, and how quickly an initially simple quantum state becomes effectively impossible to reconstruct. Yet none of this means scientists have reversed time. The laboratory clock still moves forward during the whole experiment. Researchers first perform one evolution and then deliberately engineer another evolution designed to undo it. The system does not travel into its own past. It moves through a new sequence of physical states that, if the reversal is accurate enough, ends near a state resembling the original one. That distinction matters because reversing evolution and reversing time are not the same thing. You can walk backward along a trail without making yesterday return. The Loschmidt echo is the quantum version of retracing the trail with extraordinary precision. And the deeper you think about it, the more unsettling the experiment becomes. The everyday arrow of time feels absolute because complex systems constantly lose accessible information into their surroundings. But under carefully controlled quantum conditions, some of what seems gone can be coaxed back into view. A state can spread, scramble, and fade from anything you would recognize, yet still retain enough hidden structure for an attempted reversal to make it reappear. The echo does not prove that the past still exists somewhere waiting to be recovered. It shows something more precise and perhaps more useful. Disappearance is not always destruction, and irreversibility may sometimes come not from information being erased, but from information becoming so delicately scattered that finding the road back becomes almost impossible. Quantum scars, chaotic quantum systems, can keep remembering special classical paths. Chaos is supposed to erase patterns, yet some quantum systems carry bright traces of a path that classical chaos says should be almost impossible to follow for long. These traces are called quantum scars, and they appear in systems whose classical versions behave chaotically, meaning that two nearly identical starting points can eventually lead to completely different motions. Imagine a perfectly smooth table with oddly shaped walls and a tiny ball bouncing inside it. In a simple circular table, the ball can follow neat repeating paths, but change the boundary into a shape that produces chaotic motion. And most trajectories become complicated very quickly, scattering through the available space until no single route seems special. Now replace that classical ball with a quantum particle. You can no longer describe it simply as a tiny object following one clean line. Instead, its state spreads through the enclosure as a wave. And if the system is strongly chaotic, you might expect that wave to become distributed almost randomly across the whole region. Much of the time, that expectation works surprisingly well. But in the 1980s, physicist Eric Heller noticed something unexpected while studying quantum versions of chaotic systems. Some wave patterns were not evenly spread. They showed unusually strong intensity along the locations of certain classical periodic orbits, paths that a classical particle could repeat again and again if it started in exactly the right way. The strange part is that these particular classical paths are unstable. Imagine balancing a pencil perfectly upright on its tip. In theory, it can remain there, but the tiniest disturbance sends it falling away. An unstable periodic orbit is similar. A perfectly placed classical particle could keep tracing the route, but an almost invisible change in its starting position would make it wander away into the surrounding chaos. You might therefore expect such a fragile path to become irrelevant in the quantum system. Instead, the wave function can become unusually concentrated around it, leaving a visible scar of a classical trajectory that is unstable and rare. The particle is not literally traveling around that orbit like a miniature planet trapped on rails. A quantum scar is a pattern in the probability distribution of certain quantum states. If you repeated measurements many times, the scarred regions would be places where the particle is found more often than a completely random, chaotic wave picture would suggest. The name scar is beautifully appropriate because the classical orbit itself is not the quantum object. Just as an old wound is no longer the event that caused it, what remains is a trace. To understand how that trace can form, think of a bell. Strike it once and many vibrations travel through it. Most overlap in complicated ways and fade into a complex pattern, but certain routes allow waves to return in step with themselves. When repeated pieces arrive with the right timing, they reinforce one another instead of cancelling. Something similar can happen near an unstable periodic orbit in a quantum chaotic system. A wave packet launched near that route begins to spread because the underlying classical motion is unstable, yet part of the wave can return near its starting region after traveling around the periodic path. If the returning wave has the right phase relationship, repeated returns reinforce the probability along that orbit. The system is chaotic, but the chaos has not erased every trace of its classical skeleton. Certain repeating trajectories can leave stronger fingerprints than others. This was surprising because one of the broad expectations of quantum chaos is that highly excited states in strongly chaotic systems should become rather evenly distributed over the regions they are allowed to occupy. In simple terms, if classical motion eventually explores almost everywhere, the corresponding quantum probability should often spread almost everywhere too. Quantum scars are important exceptions to that smooth picture. They do not destroy the theory of quantum chaos, and they do not mean every chaotic system is secretly orderly. Most quantum states may still look irregular and widely spread. Scars appear only in particular states and around particular unstable orbits, but their existence shows that chaos can preserve more structure than a purely random picture would predict. Researchers have found scar-like patterns in many systems, including microwave cavities designed to imitate quantum billiards, electrons moving through confined structures, cold atoms, optical systems, and other wave experiments. One famous shape used to study the idea is the stadium billiard, which looks roughly like a rectangle capped by semicircles. A classical particle bouncing inside such a shape is chaotic, yet there is an obvious unstable route in which it bounces straight back and forth between two parallel walls. Almost any tiny sideways error causes the particle to leave that path, but quantum wave patterns can still become strongly enhanced along it. You can almost see the ghost of the classical bouncing ball inside the quantum probability map. And this is where quantum scars teach something deeper than a curious visual pattern. Quantum mechanics and classical physics are often introduced as if one replaces the other completely. Large objects follow trajectories, tiny objects become waves, and the old picture disappears. Quantum chaos shows that the relationship is more complicated. Classical trajectories can continue to shape quantum states even when those trajectories are unstable, and even when the overall classical system is chaotic. The classical world leaves a kind of architecture inside the quantum one, yet you should not imagine that every possible classical path gets preserved. There are infinitely many trajectories in a chaotic system, and most do not produce prominent scars. The effect depends on how waves repeatedly return, how their phases line up, the stability of the orbit, and the energy of the quantum state. Sometimes the enhancement is strong enough to stand out clearly. Sometimes it is weak. Sometimes no obvious scar appears at all. Researchers still study exactly how these structures behave and how strongly they survive in different systems. There is also an important distinction between these original single-particle quantum scars and the quantum many-body scars found later in systems containing many interacting particles. They share the word scar because both involve unusual resistance to the behavior normally expected from chaotic quantum systems. But they are not simply the same phenomenon at different sizes. The original quantum scar is closely tied to enhanced wavefunction intensity around unstable periodic orbits of an underlying classical system. Many body scars involve a different kind of special structure and deserve their own explanation. What makes the original phenomenon so beautiful is how little is needed to produce something that seems almost like memory. The quantum system does not remember in the way your brain remembers a road. There is no stored picture of the orbit hidden inside the particle. The memory comes from repeated wave reinforcement and from the geometry of the system itself. Yet the result looks hauntingly like a path refusing to disappear. Chaos says that a traveler placed almost perfectly on the orbit should be thrown away from it. Quantum interference says that the orbit can still become one of the brightest features in the final state. So when you look at a quantum scar, you are seeing two descriptions of nature meet in an unexpected place. The classical path that should be fragile, and the quantum wave that should be spread out. Neither wins completely. Instead, the unstable path leaves a mark inside the wave, and perhaps that is the quiet lesson hidden in quantum scars. Chaos does not always mean that structure has been destroyed. Sometimes the most unstable paths are precisely the ones that leave the clearest traces behind. Quantum many-body scars. Some systems refuse to thermalize, even when everything says they should. Heat a cup of coffee, stir in cold milk, and wait long enough, and you never expect the hot and cold regions to separate themselves again into the pattern they had before. Nature seems to have a powerful habit of forgetting how things started. Physicists call the quantum version of this forgetting thermalization. When many quantum particles interact strongly with one another, information about a simple starting arrangement usually spreads through the entire system. One particle affects its neighbor. That neighbor affects another. Correlations grow. And after enough time, the original pattern becomes almost impossible to recognize by looking at any small part. The system settles into behavior that depends mainly on broad quantities, such as its total energy, rather than on the exact microscopic arrangement it began with. This is why thermalization feels almost inevitable in a large interacting system. There are simply too many pieces exchanging information for one special pattern to remain important forever. Yet quantum many-body scars reveal a remarkable exception. Certain interacting quantum systems contain a small collection of very unusual states that refuse to forget in the way almost everything around them does. Prepare the system in just the right starting pattern, and instead of smoothly losing that structure, it can move away from it and later return toward it again and again, producing surprisingly regular oscillations inside a system that otherwise behaves chaotically. The discovery became especially famous through experiments with chains of Rydberg atoms. These are atoms excited so strongly that one electron occupies a very large quantum state, making neighboring atoms interact in an unusual way. Researchers arranged dozens of atoms in a line and used lasers to control whether each atom was in its ordinary state or its Rydberg state. A crucial rule appeared because of something called the Rydberg blockade. When one atom was excited, nearby atoms were strongly prevented from being excited at the same time. You can picture a row of seats where raising one red flag temporarily prevents the next seat from raising its own. This simple restriction creates a huge number of possible arrangements. And because the atoms interact, you would normally expect a chosen pattern to quickly dissolve into an enormous sea of possibilities. Researchers prepared one particularly simple alternating pattern: excited, unexcited, excited, unexcited, and watched what happened. The system began to evolve, but instead of forgetting the pattern once and for all, it displayed repeated returns toward it. The atoms oscillated in a surprisingly organized rhythm. In a generic thermalizing system, such clear revivals should fade quickly, because the initial information spreads into countless microscopic degrees of freedom. Here, part of that information remained unusually accessible. This was not because the atoms were isolated from one another. Quite the opposite. Their interactions were essential. It was not because the system was completely integrable, meaning secretly governed by enough simple conserved quantities to make its motion predictable. Most of the system still behaved like an ordinary chaotic many-body quantum system, and it was not the same as many-body localization, where disorder can prevent energy and information from spreading through a material. The Rydberg chain did not need strong random disorder to show the effect. something much more selective was happening. Hidden inside the enormous collection of possible quantum states were a small number of special energy states with unusual structure. These states had much lower entanglement than typical states at similar energies, and were arranged through the energy spectrum in a way that allowed certain simple starting configurations to overlap strongly with them. When the alternating atomic pattern was prepared, it did not spread equally into every available state. It placed unusually large weight on this special family. Because the energies of those states were spaced in a nearly regular pattern, their contributions could repeatedly come back into step, producing the observed oscillations. Researchers borrowed the word scars because these exceptional states seem to form a narrow, organized structure inside a quantum system that should otherwise look thermal and chaotic. But many-body scars are not simply the same phenomenon as the single-particle quantum scars found near unstable classical orbits. Here, the important object is an interacting collection of many quantum particles, and the mystery is why particular many-particle states avoid the ordinary route toward thermal equilibrium. This makes the phenomenon a special form of weak ergodicity breaking. Ergodicity is the rough idea that, given enough time, a complex system explores the possibilities available to it so thoroughly that where it started stops mattering very much. Many-body scars create tiny exceptions inside that rule. Most starting states can still thermalize normally, yet a special set remembers far more than expected. It is as though an enormous city contained millions of roads arranged so that almost every traveler quickly becomes lost in traffic, but a few carefully chosen starting streets feed into a hidden loop that keeps bringing the traveler back near home. The loop does not describe the whole city. It is exceptional precisely because the rest of the city remains complicated. This selectivity is one reason the discovery attracted so much attention. If every state refused to thermalize, physicists could simply say the system obeyed some completely different simple law. Instead, the same quantum system can forget one initial state rapidly while allowing another carefully prepared state to retain striking memory. That means thermalization is not determined only by the system itself. The structure of the initial state can matter enormously. Researchers have since found and engineered scar-like behavior in several quantum models and experimental platforms, and they have learned that scars can arise through more than one microscopic mechanism. Some can be understood through approximate collective motions, where many particles temporarily behave almost like one coordinated object. Others are connected to special algebraic structures hidden inside the system's rules. Scientists can even modify interactions to make scarred revivals stronger or weaker, turning the phenomenon into a laboratory for studying why quantum systems forget. This is more than a curiosity because controlling thermalization is important for quantum technology. Quantum information stored in an ordinary interacting system tends to spread and become difficult to recover. A special subspace that naturally resists thermalization could help preserve particular kinds of coherent motion for longer times. Although many-body scars are not a ready-made universal quantum memory, and they do not protect arbitrary information perfectly, their revivals eventually decay in realistic systems because the special structure is rarely exact. Experimental imperfections accumulate, and interactions with the environment introduce further loss of coherence. The system remembers, but not forever, and that limitation may be exactly what makes the phenomenon so revealing. Many-body scars sit between two simple extremes. They are not perfectly frozen, and they are not completely thermal. They show that forgetting in quantum mechanics can depend on hidden architecture inside the space of all possible states. Most arrangements become absorbed into the statistical crowd, while a rare few continue to carry recognizable traces of where they began. You normally think that once enough particles interact, individuality disappears and only temperature remains. Quantum many-body scars tell you that this expectation is powerful but not absolute. Deep inside a system containing countless ways to lose its past, nature can preserve narrow corridors where memory survives, motion repeats, and a carefully chosen beginning continues to matter long after ordinary intuition says it should have been forgotten. Time crystals, a quantum system, can repeat in time without repeating through ordinary motion. A crystal can sit completely still and still contain a repeating pattern. So physicists eventually asked a question that sounded almost absurd. If matter can form a pattern across space, could it also form a pattern across time? That question led to time crystals, a strange phase of matter whose repeating structure is not a row of atoms arranged like bricks, but a rhythm that appears again and again as the quantum system evolves. To understand why this is unusual, think first about an ordinary crystal such as salt. Empty space treats every location equally, yet when salt forms a crystal, its atoms choose particular repeating positions. Move your attention by exactly the right distance, and the pattern looks the same again. Physicists describe this by saying, the crystal has broken the smooth symmetry of space and replaced it with a repeating spatial pattern. A time crystal applies a related idea to time. Instead of asking where atoms repeat, you watch some measurable property of a many-particle system, perhaps the orientation of tiny quantum spins, and discover that it returns in a stable rhythm. But simply repeating is not enough. A pendulum swings repeatedly. Earth goes around the sun repeatedly. Your heart beats repeatedly. None of those things automatically count as time crystals. The important feature is that the repeating rhythm represents an organized phase of many interacting particles and can break the timing symmetry imposed on the system. The clearest example is the discrete time crystal. Imagine scientists gently driving a group of quantum spins with a repeating sequence of pulses, like tapping a system once every second. If the spins merely followed the taps normally, they might repeat every second too. That would be ordinary forced motion. The system is simply copying the external clock. A discrete time crystal can do something much more interesting. Under the right conditions, the system can settle into a collective response that repeats every 2 taps instead of every tap. The laboratory says, in effect, 1, 1, 1, 1, while the quantum system answers 1, 2, 1, 2. Its own observable pattern therefore has a longer period than the force driving it. Even better, this rhythm can remain stable when the pulses are slightly imperfect. If every spin was simply performing an individually tuned trick, a small error would quickly ruin the pattern. In a genuine time crystalline phase, interactions between the particles help lock their behavior together, making the collective rhythm surprisingly resistant to small disturbances. This robustness is part of what distinguishes a phase of matter from a delicate laboratory coincidence. Experimental signatures of discrete time crystals were first reported in 2017 using systems including trapped atomic ions and spins in diamond, and related behavior has since been studied in superconducting quantum processors, cold atoms, nuclear spins, and other platforms. You can picture the simplest version as a row of tiny arrows. A pulse tries to flip the arrows. If everything were perfect, perhaps they would point up, then down, then up, then down. But real pulses are never perfectly timed, so ordinary independent arrows would gradually lose synchronization. In a suitable time crystalline system, the arrows interact strongly enough that the whole group can maintain a collective rhythm anyway. One moment, the pattern resembles one arrangement. Later, it resembles another. And only after an additional drive cycle does the original arrangement return. Nothing needs to travel around a track. No object needs to leave one location and come back. What repeats is the quantum state's organized behavior through time. This explains the strange phrase, a system can repeat in time without repeating through ordinary motion. The crystal is not a tiny clockwork machine with gears endlessly spinning. Its ticks are changes in collective quantum properties. There is also an important historical twist. When physicist Frank Wilczek first proposed time crystals in 2012, the dream was even more dramatic. Perhaps a quantum system in its lowest energy equilibrium state could spontaneously keep changing forever, breaking continuous time symmetry without being driven. Later, theoretical work showed that this original kind of equilibrium time crystal cannot exist in the simple form first imagined for a broad class of ordinary systems. That did not kill the idea. It redirected it. Physicists realized that non-equilibrium systems, especially periodically driven ones, could support a different and well-defined form of time crystalline order, and those discrete time crystals became experimentally accessible. More recent research has also explored continuous time crystalline behavior in open or driven systems, where energy exchange with an environment or external pumping changes the rules from the forbidden equilibrium case. This distinction matters because the phrase time crystal can otherwise make it sound as though physicists discovered perpetual motion. They did not. A time crystal is not an engine that runs forever while producing free energy. In many important experiments, the system is periodically driven from outside, and maintaining the experimental conditions requires real energy and careful control. You cannot attach a wire to a time crystal and receive unlimited electricity. If you try to continually extract useful work from its repeating behavior, you would disturb the system and eventually destroy the very conditions that allow the ordered rhythm to exist. The repetition is a property of the phase, not a loophole in conservation of energy. Another misconception is that the crystal itself somehow travels through time differently from you. It does not. Laboratory clocks continue normally. Cause still precedes recorded effects. The particles are not jumping into the future and returning. What is special is the symmetry of their evolution. If the external driving pattern repeats after one fixed interval, but the system's own pattern requires 2, 3, or another number of intervals to repeat, then the system has chosen a temporal structure that is different from the timing directly imposed upon it. Modern research has even explored more complicated time crystals with higher order or fractional responses, showing that temporal order can be richer than the simplest every other beat pattern. That is why physicists treat time crystals as phases of matter rather than merely strange oscillators. A normal clock is designed so that one mechanical component repeats. A time crystal emerges from collective interactions among many components and displays a kind of order that survives reasonable imperfections. The difference is similar to the difference between drawing a checkerboard by hand and watching atoms naturally arrange themselves into a solid crystal. One pattern has been individually instructed. The other emerges from the rules connecting many pieces. And this may be the most surprising lesson hidden inside time crystals. You are used to thinking of phases of matter as shapes that exist in space. Ice forms a rigid structure, magnets align microscopic moments, liquids flow. Time crystals suggest that organized matter can also be classified by how its behavior is arranged across time. Time is not turning into a physical substance, and nothing is crystallizing into little blocks of seconds. Instead, the system develops a stable temporal rhythm in much the same conceptual way that an ordinary crystal develops a stable spatial pattern. What repeats is not a journey but a relationship among quantum states. What gives the repetition meaning is not motion but symmetry. And once you see that distinction, the name time crystal stops sounding like science fiction and starts sounding almost inevitable. Matter already knows how to organize itself into patterns across the directions you can see. Under the right quantum conditions, it can organize its behavior across the direction you can never stop moving through. Discrete time crystals can keep oscillating at a rhythm the driving force never directly gave them. Give a quantum system a perfectly regular beat, and under the right conditions, it can answer with a different rhythm that you never told it to follow. That is the strange heart of a discrete time crystal. Imagine a group of tiny quantum spins being pushed by an external pulse once every second. The driving force is simple: tap, 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 always with the same spacing. If the system behaved like an ordinary machine, you would expect its response to repeat every second as well. But a discrete time crystal can do something else. It may return to the same observable state only every 2 pulses, or sometimes after an even longer repeating pattern, creating a rhythm that is a fraction of the frequency of the drive. The system is not ignoring the external force. It is using it to organize a new collective pattern. One pulse pushes the system into one configuration. The next pushes it into another, and only after the second pulse does the original pattern return. So the drive repeats after 1 step, while the system repeats after 2. This is called a subharmonic response, and it is much more important than simply seeing something oscillate slowly. You could easily make an ordinary pendulum respond every second tap by designing the mechanism that way, but a true discrete time crystal must show something more stubborn. Its rhythm has to remain stable even when the driving pulses are not perfectly tuned. Suppose the pulse is meant to flip each spin completely, but in reality every pulse is slightly too weak. If the spins were independent, those small mistakes would build up. One spin would fall out of step, then another, and the neat rhythm would quickly disappear. In the time crystalline regime, interactions between the particles can lock the system into a collective response. The particles correct one another in a sense, not by thinking or communicating like people, but because the allowed many-body dynamics favor a stable repeating pattern. The response stays close to twice the drive period even when the pulse strength is changed a little. That rigidity is one of the clearest signs that you are seeing a phase of matter rather than a fragile trick. The system has chosen its own repeating temporal structure from the possibilities available to it. Physicists often describe periodically driven quantum systems using the idea of Floquet dynamics. You do not need the mathematics behind that word. Just think of a movie that advances one frame every time the external pulse repeats. If the drive itself returns to the same conditions every frame, then ordinary behavior would also look the same after each frame. A discrete time crystal instead needs 2 frames, or sometimes more, before its observable pattern returns. The external movie loop is 1 frame long, but the system's internal story is 2 frames long. This would normally be hard to maintain because repeated driving tends to pump energy into interacting systems. Given enough time, many driven quantum systems absorb energy and lose useful structure, eventually behaving like an overheated mess where the original rhythm becomes meaningless. Time crystals therefore need mechanisms that stop or greatly slow this heating. In some early theoretical models, strong disorder helped by producing many-body localization, which prevented energy from spreading freely through the system. In other cases, especially modern experiments, the system can enter a long-lived pre-thermal regime. There, the drive is fast enough that the particles cannot efficiently absorb energy from every pulse, so the time crystalline pattern survives for a very long time before heating eventually destroys it. These 2 mechanisms are different, and this is important because not every time crystal depends on disorder. The field has grown far beyond the first simple models. Researchers can now study discrete time crystalline behavior in trapped ions, superconducting qubits, cold atoms, spins in solid materials, and other controlled quantum systems. The common feature is not the material itself, but the collective temporal order. A useful way to see the difference is to imagine a classroom where a teacher claps once every second. If every child simply claps back immediately, there is no mystery. The class is following the teacher, but suppose the children somehow organize themselves so that the whole room claps only on every second teacher clap, and they keep doing this even if the teacher's timing or clap strength changes slightly. That would be much closer to the behavior physicists care about. The children would not be producing a random slower rhythm. They would be locked into a stable relationship with the drive, one that breaks the obvious one-to-one timing pattern imposed from outside. In physics language, the system breaks discrete time translation symmetry. The drive treats every cycle as identical, but the system does not. It distinguishes between alternating cycles. One cycle becomes effectively different from the next, even though the external force repeats exactly the same way. This is why discrete time crystals are not just unusual oscillators. The rhythm emerges from the collective quantum state and remains stable against small disturbances. There is also a boundary you should keep in mind. A discrete time crystal does not invent a frequency from nowhere in the sense of creating free energy. The drive is still essential. Turn off the external forcing in most of these systems, and the time crystalline order disappears. The strange rhythm is a structured response to the drive, not an independent motor running forever. It also does not mean the system can choose any rhythm it wants. The allowed responses are strongly constrained by the interactions, the driving pattern, and the phase the system enters. A period-doubled response is common, because it is one of the simplest ways to break the timing symmetry, but more complicated responses can occur in specially designed systems. Some experiments have even explored higher order and fractional time crystalline behavior, where the repeating pattern can involve more than 2 drive cycles. Yet the central lesson remains the same. The rhythm that emerges is not directly written into the external pulse sequence. It appears because many quantum components organize themselves collectively, and that makes the phenomenon surprisingly close in spirit to ordinary crystals. A block of salt is not told where every atom must sit. The repeating structure emerges because the atoms interact and settle into an ordered pattern. A discrete time crystal does something conceptually similar, except the pattern is not primarily a row of positions in space. It is a repeated arrangement of states across time. You supply the beat, but the system chooses how many beats it needs before it becomes itself again. And perhaps that is what makes discrete time crystals so difficult to forget once you understand them. A clock repeats because it was built to repeat. A driven oscillator follows a rhythm because the force pushes it that way. A discrete time crystal is stranger. The force says 1, 1, 1, 1, while the many-body quantum system quietly answers 1, 2, 1, 2, and keeps that answer stable even when the beat is imperfect. Nature is not breaking time. It is showing that matter can organize its response to time just as deeply as it organizes itself in space. Quantum frustration. Particles can be trapped in rules that cannot all be satisfied at once. Some quantum systems are given rules that are individually simple, perfectly reasonable, and completely impossible to obey all at the same time. Physicists call this frustration, and despite the name, no particle feels annoyed or confused. The frustration belongs to the structure of the system itself. The easiest way to see it is to imagine 3 tiny compass needles sitting at the corners of a triangle. Suppose each needle has one simple preference. It wants to point opposite to each of its neighbors. Start with the first needle pointing up and the second pointing down. So far, the rule is satisfied. Now look at the third needle. To oppose the second, it should point up. But if it points up, it matches the first needle instead of opposing it. Turn it down and the problem simply moves to the other side. No matter what you do, at least one pair must be unhappy with the arrangement. The geometry has created a contradiction that no clever choice can completely remove. This basic idea appears in real magnetic materials, where atoms carry quantum properties called spins that behave in some ways like tiny magnetic arrows. In certain materials, neighboring spins prefer to point in opposite directions because that lowers their energy. Arrange those spins on a simple line or square grid, and the request is easy to satisfy. Up, down, down. But arrange them on triangles, tetrahedra, or other awkward shapes, and suddenly there may be no arrangement that makes every neighboring pair happy. The system is forced to compromise. This is called geometric frustration, and it can produce an enormous number of nearly equal ways for the spins to arrange themselves. That alone is strange, but quantum mechanics pushes the problem deeper. A classical frustrated magnet could simply choose one imperfect arrangement and sit there. Quantum spins do not always have to settle so easily. Because their states can fluctuate, several competing arrangements can remain relevant at once, and the system may continue moving among possibilities even at temperatures extremely close to absolute zero, where ordinary thermal motion has almost disappeared. In other words, cooling the material does not necessarily freeze it into one simple pattern. The uncertainty can survive because it is built into quantum mechanics itself. This is called quantum frustration. One of its most important consequences is that a material can fail to develop the kind of long-range magnetic order you might expect. Normally, when a magnet becomes cold enough, many spins cooperate and choose a repeating arrangement, much like people in a stadium all raising cards to form one giant picture. In a strongly frustrated quantum magnet, that picture may never settle. The local rules keep competing, and quantum fluctuations prevent one ordinary pattern from winning. In some cases, this can help create an exotic state known as a quantum spin liquid. The word liquid does not mean the material actually melts. the atoms can remain locked inside a solid crystal, while the magnetic degrees of freedom stay highly dynamic and deeply correlated. Even at extremely low temperatures, the spins may continue to fluctuate instead of freezing into a conventional magnetic pattern. This is remarkable because low temperature usually removes disorder. Here, lowering the temperature can expose an even more delicate form of organization, one that does not look like ordinary order at all. A quantum spin liquid is not simply random. If every spin were independently changing direction, the system would be boring noise. Instead, the spins can be strongly connected by quantum correlations, so what one part does is related to what others can do, even though there is no simple repeating magnetic pattern across the whole material. The absence of ordinary order is therefore hiding a more subtle kind of structure. Frustration also creates a landscape with many competing low-energy states. Imagine trying to place a marble at the bottom of a bowl, except the bottom is not one smooth lowest point. Instead, it is covered with countless nearly equal dents. The marble has no obvious single place to settle. In a quantum system, the state can explore this complicated landscape through quantum fluctuations and tiny changes in pressure, magnetic field, chemical composition, or geometry can dramatically alter which behavior finally emerges. This makes frustrated materials especially rich laboratories for discovering new phases of matter. Small differences in the microscopic rules can lead to entirely different large-scale outcomes. Magnetic order, unusual superconducting behavior in some related materials, complex collective excitations, or disordered-looking states that remain quantum mechanically organized. But it is important not to turn frustration into a claim that particles break logic. The rules are not contradictory in the sense that nature is asking for something logically impossible, and then somehow doing it anyway. Each interaction simply tries to lower the system's energy in its preferred way. The problem is that different interactions compete. The system must choose the best compromise available, and quantum mechanics determines how that compromise behaves. You see ordinary versions of this kind of competition everywhere. Imagine three friends sitting in a triangle where each person insists on facing away from both others. The demand makes sense for any pair, but all three demands cannot be satisfied together. The frustration belongs to the network, not to the individuals. Quantum materials can contain millions or billions of such competing relationships, making the final behavior far more surprising than the simple triangle suggests. And sometimes the most interesting physics appears precisely because there is no perfect solution. If every interaction could be satisfied easily, the system might settle into a simple, repeating state and stay there. Frustration keeps possibilities alive. It creates room for collective behavior that would otherwise never appear. That is why physicists do not treat frustration as a defect. It is often a source of complexity. The impossible demand becomes a creative force. Instead of giving the system one obvious ground state, it may give it a vast family of nearly equivalent states. Instead of freezing motion, it may preserve quantum fluctuations. Instead of producing a simple magnetic pattern, it may generate hidden correlations that stretch across the material. And this leaves you with a surprisingly deep question. You often assume order comes from rules being followed perfectly. Quantum frustration shows that nature can build new kinds of order from rules that cannot all be satisfied. The system does not solve the contradiction by choosing which law to ignore. It lives inside the competition. Every particle responds to its neighbors. Every local preference pushes against another. And the final state belongs to the entire network rather than to any single interaction. Sometimes, the most interesting structure in nature appears not when everything fits together perfectly, but when nothing can. Quantum spin ice, magnetic moments can behave like emergent particles that resemble magnetic monopoles. Break one tiny rule inside certain magnetic crystals, and the mistake can begin moving through the material as though it were a new particle carrying a single magnetic pole. That is the strange world of quantum spin ice, where the microscopic magnetic moments inside a solid can organize themselves so that disturbances behave like objects that do not exist as ordinary particles in empty space. To understand why this is remarkable, start with a familiar magnet. Cut an ordinary bar magnet in half and you do not get a north pole in one hand and a south pole in the other. You get two smaller magnets, and each one still has both a north and a south end. Keep cutting, and the same thing happens. No isolated magnetic north pole has ever been found as a fundamental particle in nature. Electric charges can stand alone. You can have a negative electron or a positive proton, but magnetism, as far as ordinary particles are concerned, always seems to arrive with north and south joined together. Spin ice materials create an extraordinary exception to that picture, not by producing a true fundamental monopole, but by making collective disturbances inside the material behave mathematically and experimentally much like one. The structure begins inside crystals whose magnetic atoms sit on a three-dimensional network of corner-sharing tetrahedra. A tetrahedron is simply a tiny pyramid with four triangular faces. Each magnetic moment in the crystal is strongly encouraged to point either inward toward the center of one tetrahedron or outward away from it. In the lowest energy arrangements, the four moments tend to follow a simple rule: 2 point in and 2 point out. Physicists call this the ice rule because it resembles the way hydrogen atoms arrange around oxygen atoms in ordinary water ice. There are many different ways to satisfy 2 in and 2 out across the enormous crystal, so the material can remain highly structured without choosing one simple repeating magnetic pattern. Now disturb one magnetic moment. Suddenly, two neighboring tetrahedra no longer obey the rule. One may contain 3 moments pointing inward and only one outward, while the other contains 1 inward and 3 outward. At first, this might seem like nothing more than 2 local mistakes, but something remarkable happens when additional spins flip. The 2 defects can move apart through the crystal. One defect behaves like a source of magnetic field and the other like a sink. To an observer studying the low-energy physics of the material, they act much like a positive and a negative magnetic charge. These are the emergent magnetic monopoles of spin ice. The word emergent is essential. There is no tiny fundamental north-only particle hiding inside the crystal. Each microscopic magnetic moment still has the ordinary dipole-like structure expected from magnetism. The monopole appears only when many spins are considered together. In the same way that a wave on the ocean exists, even though no single water molecule is itself the wave. The collective pattern becomes an object with its own useful identity. Even more interestingly, when the 2 monopole-like defects separate, a chain of flipped spins remains between them. This chain is sometimes called a Dirac string, borrowing language from theoretical descriptions of magnetic monopoles. But unlike a physical rope pulling the defects tightly together, the string in spin ice can often move and rearrange without producing a huge energy cost, allowing the 2 emergent charges to travel surprisingly independently through the material. Experiments on classical spin ice compounds have found strong evidence for these monopole-like excitations through measurements of magnetic correlations, heat flow, and how the materials respond to applied magnetic fields. Quantum spin ice adds another layer. In classical spin ice, the magnetic moments are often treated as largely fixed arrows that change only through thermal processes. In quantum spin ice, quantum mechanics allows different allowed spin arrangements to transform into one another, even when the material is extremely cold. Groups of spins can effectively rearrange through quantum tunneling processes, so the crystal does not merely sit inside one ice rule configuration. It can explore a coherent combination of many allowed configurations. That motion gives the low-energy physics an astonishing resemblance to a kind of artificial electromagnetism living inside the material. The 2 in 2 out rule behaves like a magnetic version of a rule saying that field lines cannot simply begin or end in an empty region. Break the rule and an effective charge appears. Move that defect, and the surrounding spin pattern behaves like an emergent field. Some theoretical descriptions of quantum spin ice even predict collective excitations analogous to photons. Not actual particles of visible light flying through the crystal, but wave-like excitations of an emergent gauge field that obey equations resembling those of electromagnetism at low energies. This is why quantum spin ice is so much more than an unusual magnet. It demonstrates a profound idea in modern physics. The particles and forces you observe at one scale do not always have to be the basic ingredients present at a smaller scale. Sometimes new particles and new field-like laws emerge when many simpler pieces cooperate. A crowd can form a moving wave even though nobody in the crowd is shaped like a wave. A crystal can support a sound wave even though no atom is made of sound. In quantum spin ice, a collection of ordinary magnetic moments can support excitations that behave as though isolated magnetic charges and new gauge fields have appeared inside the solid. Yet there are important limits to keep the story honest. You cannot pull one of these monopoles out of the material, place it in a jar, and claim you have discovered the fundamental magnetic monopole that particle physicists have searched for. Its existence depends on the surrounding spin ice environment. Destroy the special magnetic structure, and the quasi-particle loses the meaning that made it a monopole. Nor has every proposed quantum spin ice material been proven beyond doubt to realize the ideal theoretical phase. Candidate materials can contain additional interactions, disorder, lattice effects, and experimental complications. And physicists continue to debate exactly which compounds come closest to the clean quantum spin ice state. But the underlying lesson remains extraordinary even without exaggeration. Something can behave like a particle without being fundamental. Something can carry an effective magnetic charge, even though every microscopic component still obeys the ordinary rule that magnetic poles come in pairs. The monopole is real in the same practical sense that many quasi-particles in solids are real. It can move, carry energy, interact with other excitations, and leave measurable consequences. It simply belongs to a different level of description. And once you understand that, the crystal becomes more than a piece of matter. It becomes a small universe with its own effective rules. Deep inside it, north and south can appear to separate. Defects can travel like particles. And an entire form of electromagnetism can emerge from the coordinated behavior of countless quantum spins. Nothing fundamental has been broken. No magnetic law has secretly failed. Instead, the system has shown you something more subtle. When enough simple pieces are arranged in the right way, nature can create new objects that were never present in the original list of ingredients. The monopole was not hiding inside the atom. It was waiting inside the pattern. Fractionalization. A single quantum excitation can break into pieces carrying fractions of its properties. An electron enters a material carrying several familiar properties together. Yet deep inside the right quantum system, those properties can begin behaving as though they have gone their separate ways. This phenomenon is called fractionalization, and it does not mean scientists have cracked an electron into smaller fundamental pieces with a tiny hammer. As far as experiments show, an electron outside such a material remains an elementary particle with its usual charge, spin, and other properties. Fractionalization happens because a large group of interacting quantum particles can support new collective excitations, whose properties are divided in ways that no isolated particle can display. To understand the idea, imagine a long line of people standing shoulder to shoulder. Ask one person to step slightly forward, and that disturbance can travel along the line, even though no single person travels from one end to the other. What moves is the pattern. Quantum materials can support disturbances in a similar way, except those disturbances can behave so consistently that physicists treat them as particles of their own, called quasi-particles. Now suppose an electron is added to a very special one-dimensional system, something that behaves almost like a quantum wire. An electron normally carries both electric charge and a property called spin. In an ordinary three-dimensional metal, those features usually appear to travel together with the electron-like excitation. In some one-dimensional interacting systems, however, the disturbance can separate into two independent collective motions. One carries the electron's charge but not its spin. The other carries its spin but not its charge. Physicists often call these excitations a holon and a spinon. The electron has not been sliced into two miniature particles. Instead, the many electrons already inside the material reorganize together so that the information associated with charge travels through the system differently from the information associated with spin. If you could inject one electron at one end and watch what happens with perfect instruments, the charge-like disturbance and the spin-like disturbance could propagate at different speeds. Something that entered as one familiar package would reveal itself inside the material as separate collective pieces. This is known as spin-charge separation, one of the clearest examples of fractionalization. It is possible because one-dimensional systems behave very differently from the ordinary metals around you. In a broad three-dimensional space, electrons have many ways to move around one another. In a narrow quantum chain, they cannot easily pass without strongly affecting their neighbors. The entire group becomes involved whenever one member moves, and the simple picture of independent electrons begins to fail. The useful objects for describing the system are no longer always the original electrons, but new excitations created by their collective behavior. Fractionalization becomes even stranger in another famous setting, called the fractional quantum Hall effect. Place electrons in an extremely thin layer, cool them to very low temperatures, and apply a powerful magnetic field, and the electrons can organize into a highly correlated quantum state, unlike an ordinary solid, liquid, or metal. In this state, the elementary disturbances can behave as though they carry only a fraction of the electron's electric charge. Experiments have measured quasi-particles with effective charges such as 1/3 of the charge of an electron. That does not mean researchers found a free object carrying 1/3 of an electron's charge floating through empty space. The fractional charge exists as an excitation of the entire quantum Hall state. Remove the special environment, and the quasi-particle cannot simply continue living as an independent fundamental particle. Its fractional property belongs to the collective organization of the material. A simple way to picture this is to imagine a crowded row of seats with exactly one object in each position. Shift many objects slightly and create a small defect in the pattern. No individual object is 1/3 of its normal size. Yet the defect created by the coordinated shift can represent only a fraction of what moving one complete object would normally change. Quantum fractionalization is vastly more subtle than this picture, but the central lesson is similar. A fraction can belong to a collective disturbance even when none of the basic ingredients has been physically divided. This is why the phrase "an electron breaks apart" must be handled carefully. What breaks apart is the way its quantum numbers are carried through the system. Charge can become associated with one excitation, spin with another, and in still other quantum phases, different combinations of properties can emerge. The original particle remains part of the microscopic ingredients, but it may no longer be the best object for describing what actually moves through the material. This is an astonishing change of perspective. You normally learn physics by beginning with particles and asking what collections of those particles can do. Fractionalization forces you to reverse that thinking. Sometimes the collection creates new particle-like objects with properties that none of the individual ingredients possesses alone. And these new excitations are not merely convenient words. They can affect heat flow, electrical transport, spectroscopy, and other measurable properties. Scientists can detect their presence by studying how energy, charge, or spin travels through a material. And in some systems, they can observe signatures showing that what began as one excitation has separated into distinct modes. The fractional quantum Hall effect goes even further because its quasi-particles can possess unusual exchange behavior, unlike ordinary electrons or photons, opening the door to another family of excitations known as anyons. But fractionalization itself is the more basic surprise. The rules governing a many-body quantum system can reorganize familiar properties into new packages. There is also an important limitation. Not every material does this. Most of the matter around you allows electron-like excitations that still carry charge and spin together in a familiar way. Fractionalization requires special interactions, dimensionality, or quantum phases that prevent the ordinary particle picture from working. It is therefore not evidence that your body, a table, or a copper wire is constantly dissolving electrons into mysterious fragments. The effect belongs to carefully defined systems where collective quantum behavior remains strong enough to dominate. Yet precisely because it needs such special conditions, Fractionalization teaches you something profound about what a particle really means inside matter. A particle may be fundamental in empty space and still cease to be the most natural unit of description once it enters a strongly interacting quantum environment. The material can redistribute its properties among new excitations and make those excitations behave like independent travelers. One carries charge, another carries spin. Somewhere else, a disturbance behaves as though it carries only part of the charge you thought could never be divided. Nothing has violated charge conservation, and no fundamental electron has been cut into pieces. The accounting across the full system still works perfectly. What has changed is where the properties live. They no longer have to travel bundled together in the same familiar package. And perhaps that is the deepest lesson of fractionalization. Nature does not promise that the pieces you begin with will remain the pieces that best describe what happens next. Put enough quantum particles together, let them interact strongly enough, and the group can invent new carriers for familiar properties. What entered as one can behave as several, and the fractions are real not because the original particle shattered, but because the collective system learned a new way to carry what the particle once carried alone. Anyons. Some quantum particles. Remember how they were moved around one another. Imagine two tiny objects trading places, and after the swap, the universe somehow remembers exactly how one traveled around the other. For every ordinary object you know, that sounds meaningless. If two identical marbles exchange positions, nothing about the final arrangement tells you which marble passed on the left and which passed on the right. Even in most of quantum physics, identical particles fall into only two familiar families. There are fermions, such as electrons, which obey strict rules that prevent identical particles from piling into the same quantum state. And there are bosons, such as photons, which are perfectly happy to share. But in special systems that behave as though motion is confined to a flat, two-dimensional world, quantum mechanics allows a third possibility: anyons. They are called anyons because their behavior can lie between, or even go far beyond, the two ordinary categories. The strangest part is not simply that they are unusual particles. It is that exchanging them can change the quantum state in a way that depends on how the exchange happened. Picture two ants walking on a sheet of paper. One ant circles clockwise around the other and returns to its starting region. Now imagine repeating the journey counterclockwise. To your eyes, both situations may end with the ants occupying the same positions. Yet for anyone's, those two journeys need not be physically equivalent. The path taken around another anyone can leave a lasting mark in the quantum state. This is what physicists mean when they say anyone can remember how they were moved around one another. There is no tiny brain inside the particle storing a map. The memory is contained in the mathematics and physical state of the whole group. The important information is not merely where the anyons end up, but how their paths wind around each other on the way there. Physicists call this winding process braiding, because if you draw each particle's path through time, the lines can resemble strands of hair being braided together. This idea works especially naturally in two dimensions. In ordinary three-dimensional space, if two particles move around one another, their paths can often be untangled by lifting one root over another. A flat world gives you less room. You cannot simply lift a path above the surface to erase the winding, so clockwise and counterclockwise exchanges can remain fundamentally distinct. That simple geometric restriction opens the door to completely new quantum behavior. The simplest anyons are called abelian anyons. When one is carried around another, the quantum state gains a change that can affect later interference experiments. Almost like adding an invisible twist to a wave. Repeat the braid and you add another twist. The individual anyone can return to exactly where it began, while the overall quantum state has changed. This already breaks the intuition you learned from ordinary particles, where exchanging identical objects twice usually seems to bring you back to the same physical description. But there is an even stranger possibility: non-abelian anyons. With these, different braiding sequences can produce genuinely different final quantum states, and the order of the braids matters. Moving A around B and then B around C may not have the same effect as performing those operations in the opposite order. Imagine several colored strings lying on a table. Simply counting where the ends finish does not tell you which braid was made. The crossings themselves contain information. Non-abelian anyons can store quantum information in a similar way, except the braid belongs to the collective quantum state rather than to literal strings. This is why they have become so important in the search for topological quantum computers. Ordinary quantum information is extremely fragile. Tiny disturbances from heat, noise, stray fields, or imperfect control can damage a qubit. Information stored in the braiding of non-abelian anyons could be much harder for small local disturbances to erase, because the important information would not live in one exact particle or one exact location. It would live in the global pattern created by how several anyons have been moved around one another. To accidentally change that pattern, the environment would have to do something far more organized than simply nudge one particle. This is called topological protection. It is one reason researchers hope certain anyons could eventually provide a naturally more fault-tolerant way to perform quantum computation. But there is an important reality check. Anyons are not little exotic creatures flying freely through empty space like electrons. In the best established cases, they appear as collective excitations inside carefully prepared two-dimensional quantum materials, especially systems related to the fractional quantum Hall effect. The underlying material may contain ordinary electrons, yet when those electrons interact strongly in a flat layer under extreme conditions, the collective state can support excitations with anyonic exchange behavior. The anyon belongs to that organized quantum environment. Remove the environment, and you do not simply carry the same quasi-particle away in your hand. Experiments have produced strong evidence for abelian anyons by using devices called interferometers and by studying how quasi-particles behave when they encircle one another. In these experiments, researchers do not watch a tiny glowing object draw circles through a microscope. Instead, they measure electrical signals and interference patterns whose changes reveal the special exchange statistics. Evidence for non-abelian anyons is a much harder challenge, and although several candidate systems and increasingly sophisticated experiments have produced promising signatures, establishing and controlling them well enough for large-scale topological quantum computing remains an active area of research. So it would be misleading to say that scientists already have a mature computer filled with anyons braiding perfectly on command. The idea is powerful, the experimental progress is real, but the engineering problem is still difficult. What anyons have already changed, however, is the way physicists think about identity. Normally, if two particles are identical, you might imagine that swapping them should be physically meaningless, because there is no way to tell which is which. Quantum mechanics already makes this more subtle for electrons and photons, but anyons go further. Their exchange can itself become a physical operation. Where the particles end is not the entire story. The history of their winding can become part of the state, and that leads to an unexpectedly deep idea. Information can sometimes be stored not in the pieces themselves, but in the relationships among their paths. A single anyon cannot tell you the braid. Even knowing the final locations of all the anyons may not reveal it. The information belongs to the pattern created collectively over time. This makes anyons feel less like ordinary little objects and more like knots written into a quantum system. The knot can change when you move the pieces around, and different knots can represent different information. Nothing supernatural is remembering the motion. The laws of quantum mechanics simply distinguish between histories that ordinary intuition would treat as equivalent. You began with the innocent act of swapping two identical objects. In everyday life, a swap is almost too simple to notice. In a two-dimensional quantum world, the same act can become a way of writing information into matter. Move anyone around another, and the final positions may look unchanged, while the quantum state quietly carries the trace of the journey. Sometimes the most important thing about a particle is not where it is, but how it got there. Topological quantum memory. Information can be stored in the global shape of a system instead of any one place. Erase one tiny part of an ordinary memory device, and you may destroy the information stored there. But a topological quantum memory is designed around a much stranger idea. Hide the information so widely across a system that no single small disturbance can find it. In a normal computer, a bit lives in a specific physical place. A tiny region of a chip might represent 0 or 1, and if that region is damaged badly enough, the bit can be lost. Quantum information is even more delicate because a qubit can contain a carefully controlled combination of possibilities, and weak environmental noise can disturb that state long before anything looks visibly broken. Heat, stray electric fields, imperfect control pulses, vibrations, or interactions with nearby particles can all introduce errors. This fragility is one of the greatest obstacles in building useful quantum computers. Topological quantum memory attacks the problem by changing where the information lives. Instead of placing a logical qubit inside one physical particle, researchers try to encode it across many particles at once, using a pattern that depends on the global structure of the entire system. A useful picture is a loop drawn on a sheet covered with tiny tiles. If you slightly move one tile, the loop is still a loop. If you scratch a short section of the line, you can still tell that the overall path wraps around the sheet. To truly change the meaning of the loop, you may need to perform a disturbance that stretches across a large part of the surface. That difference between a local scratch and a global change is the heart of topological protection. In one famous theoretical model called the toric code, quantum bits are arranged on a grid with special collective rules linking them together. The logical information is not stored in any individual qubit. Instead, it can be associated with large loops that wind around the system. Imagine the surface shaped like a donut. One loop can wrap through the hole, while another can circle around the outside. These paths cannot be smoothly changed into one another without cutting or crossing a large region of the surface. Their global relationship can therefore represent information. A small error affecting one qubit changes only a tiny piece of the pattern. It does not automatically alter the logical value hidden in the full winding structure. This is why topological quantum memory is often described as storing information non-locally. Non-local here does not mean faster than light action. It means the information is distributed so broadly that pointing to one microscopic location and saying the qubit is exactly here no longer makes sense. The logical state belongs to a collective pattern. This creates a remarkable defense against noise. Most disturbances in real laboratories are local. A stray field usually hits one region. A thermal fluctuation affects a few nearby particles. A control mistake happens at one operation. If the quantum memory is designed correctly, those small local errors create detectable defects rather than immediately destroying the stored logical information. Physicists can then measure special properties of the system called error syndromes. These measurements reveal where the pattern has been disturbed without directly reading the encoded quantum information itself. That distinction is extremely important. If scientists simply measured the logical qubit in the ordinary way, they could destroy the quantum state they were trying to protect. Error syndrome measurements, instead, ask a safer question. Has the local pattern been violated here? They locate the damage without demanding to know the hidden logical answer. Once enough of those defect signals are collected, a classical computer can infer which physical errors most likely occurred and decide how to correct them. The challenge is that errors can combine. A few isolated mistakes are manageable, but if enough local errors connect into a chain that stretches across the system, they can imitate a global topological change and alter the logical information. This creates an error threshold. Below a certain error rate, increasing the size of the code can make logical failures dramatically rarer because a longer and longer chain of coordinated errors would be required to defeat the protection. Above the threshold, errors spread too quickly for the code to keep up. This is why researchers build surface codes, close relatives of topological models, using many physical qubits to protect a much smaller number of logical qubits. A single reliable logical qubit may require dozens, hundreds, or eventually thousands of physical qubits depending on hardware quality and the level of protection needed. That enormous overhead is one of the practical costs of topological quantum error correction. The phrase topological memory can therefore sound simpler than the engineering reality. The information is not protected by shape alone in the everyday geometric sense. Scientists must repeatedly measure error checks, process the results, correct mistakes, cool and control the hardware, and prevent errors from becoming correlated across large regions. Nothing about the approach makes quantum information immortal. It simply changes the kinds of mistakes that are dangerous. Local noise becomes less threatening, while large connected error patterns become the real enemy. There is also a deeper version of the dream. Instead of building topological protection entirely through active error correction, physicists search for exotic phases of matter whose natural excitations already store information topologically. In such systems, the physical state itself could provide part of the protection. This is one motivation behind research into topological quantum matter and non-abelian excitations. But a fully self-correcting quantum memory that can passively protect arbitrary quantum information for extremely long times under ordinary realistic conditions remains a major unsolved goal. Some theoretical models achieve remarkable protection in higher dimensional or highly idealized settings, while practical devices still rely heavily on active error correction. So the honest picture is not a magical memory that can never forget. It is a carefully engineered strategy for making forgetting require something much harder than one small accident. And this changes the way you think about where information exists. You are used to imagining memory as a mark somewhere. Ink on paper, a magnetized region on a drive, a charge inside a transistor, a pattern inside a neuron. Topological quantum memory asks you to imagine information that belongs instead to the relationship among many parts. Remove one part and the meaning can survive. Disturb several nearby pieces and the pattern may still be recoverable. Only a sufficiently large change across the global structure can truly rewrite the logical state. The information becomes less like a letter written on one tile, and more like the fact that an entire path winds around a hole. You can scratch the path in places, but the winding remains. And perhaps that is the quiet power of the idea. The best way to protect something fragile may not be to build a stronger box around one location, but to make the thing you care about stop belonging to any one location at all. Quantum error correction and emergent space. Space-time itself may behave like information, protected from being lost. What if the space between you and a distant object is not one of reality's basic ingredients, but something that appears only because enormous amounts of quantum information are arranged in the right way? This possibility sits near the frontier where quantum mechanics, gravity, black holes, and information theory begin to overlap. And one of its strangest clues comes from quantum error correction. Physicists are not claiming that empty space is literally a computer program running error correction software. Nor has anyone proved that our universe is built from qubits hidden behind what you see. The idea comes most clearly from a theoretical framework called holography, especially a famous example known as CFT. The central surprise of holography is that a region containing gravity can sometimes be described completely by a quantum theory living on its lower dimensional boundary. Imagine a room whose entire interior could somehow be encoded on its walls. The chairs, the air, the distance from one corner to another, and everything happening in the middle would have another description written only around the edge. This is not the same as a normal holographic picture printed on a card. The boundary theory contains all the information needed to describe the interior physics. Researchers discovered something even stranger when they asked how a particular object in that interior is represented on the boundary. You might expect one piece of boundary information to correspond neatly to one place inside, like one pixel describing one point in a photograph. Instead, information about an interior region can be spread redundantly across different parts of the boundary. In some cases, you can lose one portion of the boundary description and still reconstruct the same interior information from what remains. That pattern is remarkably similar to quantum error correction, where important information is deliberately encoded across many physical pieces so that losing a few pieces does not destroy the message. This connection was made precise in studies showing that the way local physics emerges inside holographic spacetime has the mathematical structure of quantum error correction. To see why this matters, imagine a secret sentence written not on one sheet of paper, but distributed across 5 strange books. No single book contains the sentence in readable form, yet several different groups of books can each reconstruct it. Burn one book and the sentence survives. Burn another instead and it still survives. The information is real, but asking exactly which book contains it gives you the wrong picture. Holographic theories suggest that some information describing a place inside space-time can behave similarly. A particle deep in the interior may be reconstructible from one sufficiently large boundary region, but it may also be reconstructible using a different region. There is no contradiction, because the interior particle is not being copied into several independent particles. Quantum mechanics forbids perfect copying of arbitrary unknown quantum information. Instead, the same logical information has multiple equivalent representations inside a larger encoded state. Just as a quantum error correcting code can let different sets of physical qubits recover one logical qubit. This gives physicists a new way to understand a problem that would otherwise look impossible. If the boundary is the fundamental description, how can a smooth three-dimensional interior exist at all? Quantum error correction suggests that being located inside may arise from the pattern in which information is encoded. The interior position of an object may correspond not to one fundamental storage site, but to which collections of boundary information are capable of reconstructing it. The deeper an object lies in the holographic interior, the more widely its information can be spread across the boundary in certain models. In that sense, depth itself begins to look connected to redundancy. Space is no longer merely a container where quantum information sits. The organization of quantum information may help define what the container means. A beautiful toy model known as the Happy Code made this idea easier to visualize. Researchers built a network of mathematical building blocks arranged roughly like tiles filling a disk. Information placed in the center is transformed and distributed outward until it reaches the boundary. The network acts like an error-correcting code. Erase some boundary pieces, and interior information can often still be recovered from another region. At the same time, the geometry of the network resembles important features expected in holographic spacetime. It is only a simplified model, not a miniature universe, but it demonstrates that geometry-like structure and quantum error protection can arise together from one information processing pattern. This connection also changes the way physicists think about losing information. Suppose part of the boundary becomes inaccessible. If information about an interior region had been stored at exactly one boundary location, that interior region should disappear from the description immediately. Instead, the error-correcting structure can allow the interior information to survive moderate loss. Different boundary regions can reconstruct different portions of the interior, and the region that can be reconstructed grows or shrinks depending on how much boundary information you control. Physicists call the relevant bulk region an entanglement wedge. You can picture it as the part of the interior whose information is available from a chosen portion of the boundary. Increase the boundary region, and its recoverable interior region can reach deeper inward. Reduce it, and some of that interior becomes inaccessible. This does not mean someone holding part of the boundary literally watches chunks of space vanish. It means that within the holographic description, access to interior information is organized in a way that closely resembles recovering encoded quantum data after pieces have been erased. That resemblance is not decorative. It has become one of the central tools for understanding how bulk information can be reconstructed in holography, and why local interior physics can remain consistent, even when its boundary representation is spread across many places. Entanglement seems to be another crucial ingredient. In these theories, the pattern of quantum entanglement on the boundary is deeply connected with the geometry inside. Change the entanglement enough, and the geometry can change with it. In simplified models, reducing connections between parts of the boundary can make the interior geometry stretch, pinch, or effectively separate. This has encouraged physicists to explore the possibility that spatial connectedness itself may emerge from quantum entanglement. Again, this is not evidence that you can change the shape of your bedroom by thinking differently or entangling two laboratory particles. The claims apply to specific theoretical models of quantum gravity, but within those models, the message is extraordinary. Distance may not be fundamental. The smooth interior may be a higher-level description of relationships among quantum degrees of freedom. And quantum error correction may explain why that emergent world is surprisingly stable. If every tiny disturbance to the underlying quantum information produced a huge tear in spacetime, a smooth classical world would be almost impossible to maintain. An error-correcting structure provides another possibility. Small changes in the microscopic information need not immediately change the logical information describing the interior. The geometry can be protected against certain local losses or disturbances. In roughly the same way, encoded quantum information can remain intact when some physical pieces are damaged. This does not mean spacetime can repair a cracked planet or magically reverse gravitational destruction. Error correction here describes how the same interior information is redundantly represented in the underlying quantum theory. It is a statement about encoding, not a cosmic healing mechanism, and there is a major limit you should keep in mind. The clearest version of this story comes from anti-de Sitter spacetime, a type of universe with properties very different from the expanding cosmos you actually inhabit. Our observable universe is not known to be anti-de Sitter space, and physicists do not yet possess an equally complete holographic description of realistic cosmology. So it would be dishonest to conclude that scientists have discovered the source code of space. What they have discovered is a deep mathematical relationship. In our best understood examples of holographic quantum gravity, the emergence of an interior spacetime and the protection of quantum information are intertwined in a way that is hard to dismiss as coincidence. That leaves you with an extraordinary reversal of perspective. You normally imagine space first. Objects exist somewhere. Information is stored inside those objects, and connections stretch between different locations. Holographic quantum error correction invites you to turn the order around. Perhaps the information and its relationships come first. Perhaps redundancy, entanglement, and patterns of recoverability determine which degrees of freedom behave as though they are nearby, which behave as though they are far apart, and which collections form something that looks like a smooth interior world. Space would then be less like an empty box containing information and more like the shape taken by information when it is organized in a particular way. We do not yet know whether nature truly works this way outside the special theories where the mathematics is strongest.